non-smooth, convex, and also non-convex optimization. And recently also going into machine learning. So please, the stage is yours.
Thank you very much, Benjamin. Thank you very much for the invitation. So good morning, everyone. I'm very happy to be here to speak in front of you. Maybe a little bit more about myself. I studied in Graz Telematik. Telematik is some mixture between technical mathematics and electrical engineering. And in the end of my studies, I started to focus on computer vision, image processing, and also machine learning. And then I did also at TU Graz a PhD thesis, where I already started to deal with variational methods. I will later explain to you what variational methods means. More precisely on the total variation, which will also be part of today's lecture. And then after I have completed my PhD thesis, it was in early 2008, then I moved to the University of Bonn, where I was a postdoc, and then I turned back to Graz, and now I'm a professor at TU Graz since 2014. I would be interested in to whom I'm speaking here. So who is doing computer science here? Okay, 2 persons who's doing mathematics. Okay. Who's doing engineering science? And did I miss something? Physics, okay, great. Sorry? Okay, great. So for me it would be great if we can do this, like a discussion, and if you have questions, you're of course invited to ask me and to stop me whenever you don't understand anything. And I will also try to ask you something, to try to get you the ideas, grasp the main ideas behind that, and yeah. Good, so let's start. As I said, I'm dealing with computer vision, and computer vision somehow tries to mimic what we are doing every day with our eyes and with our brain. So we are observing projections of the 3D world of our 2 eyes. Can look like this, like a video stream. And what humans are particularly well in, they can very effectively infer properties of the 3D world. So I can easily walk around, I grasp the 3D structure, I can recognize objects, faces, motions, colors, and so on. And actually this is exactly what computer vision is doing. I have these observations, images, and I would like to determine unknown model parameters based on this observed data. Here, for example, I will later talk about an algorithm that can produce from a video sequence a 3D model. So this would be the 3D structure, but you could also be interested in the colors, in the coloring of the 3D objects, also called albedo. And this is, as you can easily see, a very complicated problem, because it's an inverse problem, and when we have these projections of the 3D world to the image plane, we lose a lot of information actually. So this is a well-known thing. It's an illusion. What you see here, you are standing at a certain point in space, and you look to a mirror, and in the mirror, the reflection you're seeing is a piano, obviously. But obviously, the object that has caused this reflection in the mirror is not a piano. It's just a clever arrangement of different objects. As you can see here, look, this should be the keyboard, such that you're exactly standing on a certain point, you exactly observe a piano. So it means just seeing a piano doesn't mean it is actually a piano. So it's a highly ill-posed problem, of course. One particular nice framework, which comes from statistics, to infer properties based on observations is Basin inference. It's actually the very basis is the Bayes theorem, and it tells you basically that, so what we assume here is that F will be our given data, our given observations. It doesn't matter if this is an image, if this is a number, or this is a video, or whatever, 3D volume. And we would like to get a posterior probability of our unknown solution U. Again, it doesn't matter what this is. Could be a class of an object. It could be a clean image, could be an MRI reconstruction, whatever. And Bayes' theorem tells us, based on the definition of a conditional probability, that the posterior probability, so the probability of u given f, is proportional to the likelihood. It's the probability of f given u. So this means how well can I explain my observed data when I have found the solution, times the prior probability of u. And of course the key challenge, this is a simple formula, as you can see, but the key challenge is the application of this formula to real-world problems. And this actually means we need to find good models to model the data likelihood probability and also the prior probability. So that's the key challenge. And actually, this lecture is more or less about what are good models in computer vision and image processing for this guy and for this guy here. So what is so difficult about images? So why, for example, is it difficult to get a prior distribution of images? The thing is that there is an combinatorial explosion, which is tremendous. So if you consider discrete images of n times n pixels, and we assume that each pixel can take a gray value between 0 and 255, so 256 different gray values, then with one pixel we can generate 256 different images. With 2 times 2 pixels, you can already create 4.3 to the power of 10 to the 9 different images. And with 4 times 4, it's 3.4 times 10 to the 38, and so on and so on. And you see, even for these small images of 16 times 16 pixels, you can create a vast number of different images. So therefore, it's clear I cannot just store all reasonable images in a database, because even for 4 times 4 images, it's unfeasible. So we need to find clever formulas that somehow can tell us, is this an image with a high probability as being a natural image or a medical image or not? And you can easily see that actually only a very small fraction of this different number of images correspond to real images, and we would like to distinguish between good images and bad images, or assign a probability what is a good image and what is a bad image. So in order to put these numbers here somehow into context, do you know what's the estimated number of atoms in the observable universe, roughly? You're from physics, you should know. What do you estimate? 10 to the? Different estimates?
10 to the 38, possibly.
More estimates? So we had 10 to the 1000 or 1000, 10 to the 38. So it's somewhere between 10 to the 78 and 10 to the power of 82. So you see, this is already, you can create much more different images of size 8 times 8 pixels than you have atoms in the universe. So also for example, in chess, the game tree complexity is also known as the Shannon number, is estimated to be at least 10 to the 123. So the game complexity of chess is even much smaller than 8 times 8 images. Okay, as I said, only a small fraction of all possible images actually represent natural images. The rest will be just noise or strange images. For example, an image which just has one white dot in the middle, it's not really an useful image. Or an image of Gaussian noise, it's not useful. But there will be, of course, images that define useful structures. And there are some works who try to visualize actually what is the distribution of natural images. But you can easily see, since this is high dimensional, it's very complicated. It turns out we can do something for 2 times 2 images. And this you can do as follows. You take 2 times 2 image patches. Image patches mean you take an arbitrary image and you extract all 2 times 2 patches from this image, or from many images if you want. And 2 times 2 is still 4 dimensions. We cannot visualize a 4-dimensional intensity function, unfortunately. But what you can do, you can start to exploit some invariances of images. So images are usually invariant with respect to adding an intensity. So if you have an image and you add to all image pixels a certain intensity, the image will not change. So it's just different. It's like switching on or off the light. So what you can do, you can say, okay, take all these patches, which are 2 times 2, so therefore they are an element of R4, and I subtract the mean. So I assume that all patches have 0 mean. And with that, I can already remove one of the dimensions. So I have now a 3-dimensional function. And additionally, I can also assume that the Euclidean norm, the L2 norm, is 1. Simply by taking a patch and dividing it by its L2 norm, then I have achieved that the 2 norm is 1. And then actually it turns out that I get a distribution on the sphere, the surface of the sphere here. Okay, and this is what I did with a PhD student some years ago, just for fun, because more or less it is already done in this work by Lee, Peterson, and Mumford. Mumford is a big name in vision, so he came from mathematics, from algebraic geometry, and he also received a Fields Medal in mathematics, and then at some point in his career he turned to vision, and he did a lot of very nice contributions in vision. We will later come back to one of his works then. So with this we can visualize it actually the density of different patches on the surface of the sphere here. And you see the brighter structures correspond to more frequent patches, and the darker regions correspond to less frequent patches. You can also unroll this surface here, then you get this here, and you see actually there's a lot of structure. So 2 times 2 patches of natural images, they're not arbitrary. So actually there's a very nice structure here. This usually corresponds to rotations, because if you have an image edge, you have a rotated edge, and so on and so on. And the idea is now, of course, how can we find a good function that measures the probability of a 2 times 2 patch being a good patch or not? Yeah?
So, didn't you reduce the dimension 2 times?
Yes.
But you're still...
Then I'm on a 2D surface.
Okay.
Okay? So actually what I did, this is 3D, then I projected everything onto the surface of the sphere. Everything that has a smaller norm goes to the surface, everything that has larger norm goes to the surface. Okay? So this is, in this sense, you are just considering high contrast patches. You're not interested in low contrast patches. So no night images, just daylight images. Okay, so what about a little bit more about the distributions? It is quite standard to consider exponential distribution. So what you usually assume, and this comes from statistical mechanics, that for example, the prior distribution is proportional to the exponential of minus some energy. So you're connecting a probability with an energy. So here I don't give you the partition function here, so it's just proportional. And also the data likelihood is also proportional to the exponential of minus some data fidelity term that measures some energy distance between u and f. Could be quadratic distance, for example. So in the statistical approach, P of u is called a prior distribution, but then when we talk in terms of the energy, so R of u, we are talking about regularization term or smoothness term then later. And for the data likelihood, similar, this is in the statistical way, the data likelihood, and then when we talk about this D here, then it's called the data fidelity or data fitting term. So using Bayes' theorem, we know it's the product of prior and data likelihood. So multiplying those two exponentials means we have to sum up those two terms here. We get the following posterior distribution. The probability of u given f is proportional to the exponential of minus e, and minus e, or e, is then simply the sum of a regularization term and a data fidelity term. And this e of u and f is called the energy of the configuration. And of course, for us, in order to find a u that achieves a high probability here, this is exactly equivalent by taking the negative logarithm by finding a u that minimizes this energy here, roughly. Okay, so when we talk about inference, the Bayesian approach, it doesn't give us a single answer, doesn't give us a certain u, it gives us a complete distribution. And now the question arises, which sample from the distribution should we select? So there's no unique answer to that, of course. When you have different distributions, posterior distributions, I don't know, they could look quite differently. So if your distribution looks like this, it's quite obvious which sample to select. Maybe you select the sample with the highest probability, but sometimes a distribution could also look like this one. So this would be the sample that has the highest probability, but it's quite isolated. So maybe you would like to take more this example here or something like this. Or what happens if your distribution looks like this? Which one would you then select? One of these guys. So it's not so obvious which one is the best. And therefore, inference is basically defined in terms of a loss function. So this is a general form of a Basin estimator, and you say that my estimate u hat is that sample u that minimizes across all different solutions v a certain loss function between u and v times the posterior probability of v. Okay? So the simplest case would be that the loss function is just the quadratic difference between u and v. I think I'm writing it down on the slides. Yes? So if L of LuV is just the quadratic difference, what do you think what would be then the solution to that? So I have a big integral about all images, all 10 to the 7 million different images of this quadratic difference times the posterior distribution. So just, and now you want to select that sample u that minimizes the quadratic distance to all these v's, weighted by p f given v given f. What do you think? What's the solution? The intuitive solution. Whenever you minimize something quadratic, you get an average. Okay, so this is exactly the definition of the expectation, what I'm having here. So when you take this thing here, so you want to minimize with respect to u minus v squared. So I can put 1/2 here, just to scale it, times p of v given f, and over all v's here. When you differentiate this, it's a minimization problem, you differentiate this with respect to u. What do you get? You get integral u minus v times p of v given f. Now you set it to 0, because you want to get the minimizer of that. And then you easily see that you can get out u here. So it is u times integral p v given f dv equals integral v p of v given f dv, and then you just need to divide to get out the u here. And from the formula, actually, we see that what is u? It's exactly the weighted average. So you take every sample v, you multiply v with its posterior distribution, and you sum that up. So instead of course, you need to do the integral, but in a discretized sense, you sum this up, and then you divide by the total sum of all your posterior distributions. This is exactly the weighted average, which is the expected value. And the expected value makes sense if you have something, a distribution like this. Here it doesn't make too much sense. The expected value could give you a sample very low probability, but in most cases it makes very much sense. One problem is that this guy is very hard to compute. So you see it's the integral over all different images V, and we know that we have many images, 10 to the something, different images, and therefore this thing is very hard to evaluate. So somebody of you have heard about Markov chain Monte Carlo from physics, yeah? I guess. So this is actually an algorithm that tries to approximate this thing here by sampling in regions actually where P is larger, because you can ignore a lot of the space where this P is very small. So you try to get in these regions where you have a high probability and try to approximate this huge integral here in, by just sampling in regions with high probability. But these are very strange algorithms. I never understood them, to be honest. But they seem to work in some cases. Another possibility for the loss function is now to choose the 0-1 loss function. So here we had the quadratic loss function, but you can also take the 0-1 loss function. The 0 loss function says L is 0 if U equals V, and L is 1 if U is different from V. So it's just saying they are equivalent or not. And then it turns out, when you think carefully, when you put here 0-1, since you want to minimize, then exactly that sample that has the highest probability is left out, because you want to minimize, and this sample that is left out is exactly that sample that maximizes the posterior distribution. Okay, so with the 0-1 loss function, actually, you can turn this huge minimization problem in getting that U that maximizes the posterior distribution, and this is exactly that sample that achieves the highest probability, here it's non-unique, you can take any of them, and so on. And actually by maximizing the posterior distribution, you can also equivalently minimize the negative logarithm of the posterior distribution, and then we are back to this case where I would like to find that U that minimizes the sum of the regularization term and the data fidelity term. This is exactly what I said. This estimate with the 0-1 loss function is called the maximum a posterior estimate, also map estimate, known as map estimate. And this can be equivalently written by taking the negative logarithm as that sample U that minimizes the sum of the regularization term and the data fidelity term. So very often in this talk, we will have a fixed choice for our data fidelity term. Namely, it will be, not always, but in most cases, it will be a quadratic difference between your observed data F and A times U, where A is a linear operator, so-called forward operator. When you think in terms of inverse problems, A will be the forward operator of your inverse problem. For example, if you're doing magnetic resonance image reconstruction, where you have measurements in the Fourier domain, then A will of course be just a Fourier transform. It's a linear operator. So it tells you, I take my reconstructed image U, I apply a Fourier transform, then I get the Fourier coefficients, and they should be close to the measured Fourier coefficients. In computed tomography, CT, the linear operator will be a radon transform. So it means taking the CT image, applying the radon transform, and then it should be close to the measurements of your CT machine. What else? If you just do image denoising, then A will be the identity. So we will stick to this problem in the beginning. If you do deblurring deconvolution, where we have as input a blurry image, so F would be a blurry image, then A is just a blur kernel, and so on and so on. So the content of this lecture today will be to talk about the modeling, what are good models for, mainly I talk about R of U, but sometimes also about this data fidelity term. But the data fidelity term is mostly given by the application. As I said, for MRI it's Fourier transform, for CT it's a radon transform, for denoising it's identity, for deconvolution it's a blur kernel, and so on. So this is more or less always given. And we will discuss different choices for the regularization term. So I will start with the very basic ones, like the total variation, and then I will further develop this up to that we apply machine learning techniques in order to learn better regularization terms from data. And I will always show you applications in computer vision. This will be mainly image processing, will be stereo, 3D reconstruction, optical flow, which is motion estimation, and also some medical image reconstruction tasks. Okay, so let us start with the first thing, which is the total variation. This is actually was the topic of my PhD thesis, to use this regularization term and apply it to different problems in computer vision and to study fast optimization algorithms for that. And it is motivated by the following fact. I mean, that you can get different motivations for this, but when you think about simple images, so this is a quite abstract simple image. It consists of 3 objects. What are the 3 objects? What is this one? Yes? You see how good our brains are. Look, these are so abstract images, but you immediately grasp what this is. What is this? Ein Straußenei, maybe, if this is a bottle. A plate, yes. And this? Yes, good. Apple or orange. I mean, this is okay. We don't have to be too specific, but you see how well our brains work actually, and we are still. Computer vision is still far away from our brains. This I have to admit. Okay, so when we think about images like this, of course, natural images will be much more complicated. They will have textures, oscillating patterns, small-scale structures, but more or less on an abstract way, this is already good enough to make you understand this image, as we have seen. So the question is, what is a simple property of images that we can exploit? When we just consider the color, maybe the color is not a good information because I can easily change the background color, or the bottle color, the plate, or the apple orange color, and you will still see this is an image and doesn't disturb you too much. So it should be more or less independent of the color. And if you want to get rid of constants, what do? You apply the first derivative, right? So the first derivative makes you getting rid of constants. And if you do so, if you apply the gradient operator here just means the derivative in x and y direction, so the spatial derivatives. So we have 2, therefore it's a gradient. And for example, taking the magnitude of the gradient. And on the right-hand side, what you see is an image of the magnitude of the gradient. And the gradient is high if there's a high contrast. So between the white plate and the black background, there should be a high gradient. And it should be a little bit less if the contrast is less. And therefore, we see the magnitude is high here, and it's a bit less high here. So what I have here ignored, that I have a function, an image function that jumps. Normally, you should say, hey, stop, you cannot compute the gradient. And of course, you are completely right. The gradient does not exist. But we will see that there is an alternative definition of the gradient based on duality, actually, that can get rid of that. So now when we have plotted this image here of the magnitude of the gradient, actually, what do we see? The gradient, the magnitude of the gradient is 0 almost everywhere. So almost everywhere it's 0, and it's just on a few regions where the gradient is on. And these regions exactly correspond to the boundaries of the objects. Okay? And if you now consider a noisy image, instead of that, you will easily see that gradients will be almost everywhere because the image will have a lot of variations, and it means that this gradient image would have a lot of gradients. And therefore, one simple idea is that we define a regularization term that simply integrates over the image domain all those gradients, the magnitudes of the gradients, and we would like to minimize the integral of the norm of the gradients as a regularization term, because we know if we want to have a reasonable image, a clean image, then the total integral of gradients should be small. And if the image would be noisy, then the total integral of gradients would be high. Okay? So it's the integral over the image domain, the Euclidean norm of the gradient, and integrated over the domain. In the discrete setting, it just means summing up this image in x and y. Just sum it up. That would be the discrete approximation of this integral here. And actually, by minimizing this term here, what you are doing is you enforce sparsity in the edges. And sparsity in the edges means that there should be objects in the image that have constant color, and only at a few positions there should be a jump between the object and the background. So it leads more or less to compact objects in your image. And actually this leads to the definition of the so-called total variation. It's called the total variation because it integrates the local variations in the image. And it has been introduced to image processing in this famous work of Rudi and Osher Fatemi, 92, and more theoretically worked out by Jean-Paul and Lyons. Pierre-Louis Lyons is also a big name in mathematics. So Antonin is very well known in mathematical imaging. And actually the total variation of U is more or less this thing here, but in a mathematically more precise way, it's the integral of the distributional derivative. And the distributional derivative means that, as I said, if you have a function that jumps, the gradient does not exist, but the distributional derivative, it somehow partitions the usual gradient into a continuous part, actually where you can differentiate, and the jump part. And it just measures the height of the jump in these regions where the gradient does not exist. And by means of partial integration, you can rewrite this term here as the integral over omega of u divergence of phi. Phi is a vector field. So it's a two-dimensional vector field, which should be continuously differentiable and has compact support. And locally, it is constrained to have a 2 norm less equal than 1. Okay? And the thing is the following, that as you can see here, now we do not need to differentiate the image u. Okay, so it's just u times divergence of phi. And we just assume that phi is differentiable. And therefore, this definition is also valid for images in L1. Images in L1 means they are absolutely integrable, and we don't care about jumps there. And so the intuition about this formulation is the following. So if you have a local image gradient, okay, now my question to you is, we just consider one point, right? Which phi, whose length is less equal than 1, actually takes the supremum of this expression here. So by the Gauss integral theorem, you can rewrite this as nabla u times phi. So u diff phi is equal locally as minus nabla u times phi. Now the question is, which phi actually achieves this supremum? Okay, so nabla u is fixed. Which phi, which has norm less equal than 1, takes the highest value? How does phi have to look at? So actually it will be the phi, it's not the parallel one because I don't have a minus here. It's that one that points in the opposite direction and has norm less equal than 1. So actually it has exactly norm equals to 1. Okay, so this is nothing else than a dot product. And how does phi look like? It should point in the opposite direction. It has norm less equal than 1. So you can therefore define here, if everything is nicely differentiable, that phi is nabla u divided by norm of nabla u with minus. Okay, so that's the definition of the total variation for images that also have discontinuities. And the good thing is that in terms of variational analysis, it's first of all, it's convex. Why is it convex? Because it's a semi-norm. Every norm is convex. And convex means that we can do optimization and have some guarantees to find a good approximate global solution to it. And it's also lower semi-continuous, which allows to show that actually a solution exists. So just a few words about the space BV, which is the space of functions with bounded variation. And this is considered as being one of the most suitable function spaces for image processing. And it is defined as the follows. So BV of omega, omega is the image domain, consists of all images which are absolutely integrable and whose total variation is less than infinity. Okay, so it means you should not have too high jumps or too many jumps. So if your image consists only of jumps, of course, then this total variation will be infinity. But as soon as the total variation is less than infinity, then you're in the correct space, actually. And you can also show that this is a Banach space equipped with this BV norm, which is the L1 norm, plus the total variation semi-norm. So something what is important, the norm I'm using here, which is actually the same norm, just the dual of it used here, is quite arbitrary. I can take any norm. Yeah, so in the most simple case, you take the Euclidean norm, but it doesn't change anything if you take the infinity norm or the L1 norm or some norm involving some metric, some Frobenius norm if you have vectorial images, whatever. Okay, for us, it is also important because when we talk about images, usually we don't really deal with sharp jumps. We usually get discrete approximations with basis functions such that everything is nicely differentiable. Then it means that the total variation, if u is differentiable, it's just the integral of the norm of the image gradient. Just in case you really have sharp jumps, then you have to stick to this more involved formulation here. The total variation is also a very nice geometric interpretation. So when you decompose an image by means of its level sets. So level sets means you take the image, you threshold it at a certain value, and you take the boundary of the set that is obtained from the thresholding. And then you get, when you do this for all different thresholds, you can draw the boundaries of all the different sets obtained from thresholding, and you get this level set image here. These lines are also called isophotes. So it means along these lines with same color, the intensity value of an image is constant. Okay, so it's the lines in the image with constant intensity value. And then it turns out that the total variation is nothing else than integrating up across all different thresholds the length of all these boundaries, so the perimeters of all these boundaries. Okay? So it means taking the length of this guy plus this guy, always of course weighted by dt. dt is the step in the thresholding, infinitesimal small. And when you do this, actually what you obtain is exactly the total variation. So the total variation can also be interpreted as the total amount of the level set perimeters. So why is this interesting? It is interesting because if I consider images which are just characteristic functions, so binary images, and in binary images, obviously all thresholds between 0 and 1 will give you exactly the same level sets. Okay? So it means that the total variation on binary images is nothing else than the length of the boundary of the set that is described by this binary image. So it means I can, by minimizing the total variation, I can minimize the length of the boundary of this set that is described in this image here. So this would be an image, with quite a fractal shape. So it has a very long boundary, But when I start to minimize the total variation, I will get this. And if I further minimize the total variation, I will get this. So I can, yeah?
By the image being described by, or the set being described by the image, you mean the black parts? Or what do you mean?
It's a characteristic function, so it's usually this 1s image. 1s means it is 1 if x is in the set and 0 else. So the set is there, the y. But this is arbitrary. You can also say it in your way. It doesn't matter if the set is the black or the white part. Completely arbitrary. So therefore, you see, you can use the total variation for shape optimization. So you can try to get more compact shapes. This is also one of the disadvantages of the total variation. So when you start to minimize the total variation, it makes the length of the boundary smaller and smaller. So it has a shrinkage bias. So when we use this for image segmentation, for example, it will also always try to find segments in an image with a short boundary. But you can also do minimal surfaces with that, for example. Do you know the catenoid? Everyone knows the catenoid? So when you are in 3D and you fix a boundary value like this, so for example, you have two rings and you put a soap bubble, what comes out? Exactly the catenoid. And what's the shape of the catenoid? It somehow looks like this, right? So this is the surface with the smallest area. So what I did not mention, everything I'm saying about length of the boundary, it's true in any dimension. So in 3D, it's then the surface area. So it means if you put this as a boundary condition, being white here, and then you start to minimize the total variation by saying it should find an object with smallest surface area, it will exactly give you the catenoid. So everything you can do with the soap bubble, you can also do with the total variation. I will later show an 3D experiment for that. Okay. So now let's try to apply the total variation for our first image processing problem. And this is actually the Rudin-Osher-Fatemi model, which I have already explained. So here you see a snapshot of the original paper of Rudin-Osher-Fatemi. You see 92. It was published in a physics journal. So people started to work in physics with this thing. And the ROF model, ROF stands for Rudin-Osher-Fatemi model, is defined as the following minimization problem. It minimizes the total variation as a regularization term, and it has a quadratic fidelity term. Okay, so given a noisy image F, we try to find, by minimizing, an image U which is close in the least square sense to F, so it should not deviate too much, allows for some deviations but not too high, and at the same time should have a small total variation. And this parameter lambda here can be used to tune this trade-off. So if lambda is almost 0, then U will be F, clearly, because then this term is ignored. If lambda is very high, then actually U will deviate a lot from F, and it will only have the main boundaries of the image in it. And this model here has defined the prototypical optimization problem in mathematical image processing. So many researchers dealt with this problem. There are many questions that are still open. For example, what is a good discretization? I will shortly talk about how to discretize this. But of course, using finite elements and so on, you can get better discretizations. Then the next question will be, how can we efficiently compute a minimizer? So one problem which we'll see is that this is a semi-norm, and norms are not continuously differentiable. They are non-smooth. So how can we still find an algorithm that can compute the exact solution of this problem? And of course, different applications. We can exchange the quadratic fidelity term by L1 norm or different terms. I will talk about this later. So when we will see, when we test this on images, how well it works. It works. Let's say it works, but it's not great. So it's not a model that gives you state-of-the-art results for image restoration. It works quite well given its simplicity. You see, it's just this simple guy here. But it defines, in the end, a good trade-off between simplicity of the model and its denoising quality. Discretization. So before we can start solving this model, we need to think about how we can discretize it in order to simulate it. So usually what we're doing is we say, okay, we don't have a continuous image function. We have an image which is discretized on a regular grid. And what we assume is that we have given an m times n pixel grid. So we can say u is an element and f is an element of r m times n, r to the m times n. So each pixel can take a real value, and we have m times n different values. So with this, we can easily, approximate this quadratic norm here by just taking the sum over all image pixels and taking the quadratic difference of the corresponding image pixels. What is a bit more complicated is how we can discretize this term here. And what I'm doing here is the most simple thing you can think of it. We just take finite differences. So, the basic idea is the following. When we talk about derivatives of a function, f prime of x is the limit of h going to 0 of f of x plus h minus f of x divided by h. So I hope everyone knows this. And what we are doing, we just don't let h go to 0, but just say h should be the size of an image pixel. This is what we're saying. So, and assuming the size of an image pixel is 1, we just say h is 1, and we take the image function at x plus 1 minus the image function at x divided by 1. And since we need this in horizontal and vertical direction for the image gradient, we get these two formulas here. You see the derivative in the horizontal direction is uij plus 1. This is this plus h minus uij. This is just to make sure that we don't go over the boundary of the image. So at the boundary, we assume that the derivative is 0, which corresponds to natural boundary conditions, Neumann boundary conditions. And you do exactly the same in the vertical direction. You take, again, finite differences here. So this is really the most simple thing you can do. There's nothing simpler how to approximate derivatives on images. Okay, so then it turns out that the discrete Roth model can be written like this. So here you have the quadratic difference. The integral in the continuous definition of the norm is just replaced with a sum over image pixels. And here we now take the so-called mixed 2-1 norm of du. Okay, so just going back, this gives you, for each image pixel, two components. The first and the second. One is the horizontal difference, and the second one is the vertical difference. And what we are now doing is we want to take the 2 norm, the Euclidean norm, with respect to these two components at each image pixel, but we would like to take the 1 norm with respect to the entire image, so summing up the local contributions. And this 2-1 norm is nothing else than the sum over all image pixels. I and j is horizontal and vertical components. Then we take the square root of the sum of the local components, k is 1 up to 2 squared, and this is actually the Euclidean norm locally of the image gradient. Okay, and for short we will write for this 2-1 norm. Okay, so same as in the continuous setting, this problem is convex. Quadratic norm is nicely convex, it's a quadratic function. This is a semi-norm, it's also convex, but it's non-differentiable, it's non-smooth. And actually this is where I don't know how many papers, but a few hundred up to a few thousand, I guess, people tried to find efficient algorithms to solve this kind of problems. So what were they doing? The problem is that the square root is not differentiable, so people added a small plus epsilon here to round it at the kink at 0, or they did other different stuff to make it smooth, and then you can apply gradient descent and so on. But it turns out actually that you can, you do not need to smooth this problem by making use of duality. And therefore I have included here this small interlude about non-smooth convex optimization. So as Benjamin told you in the beginning, so part of my work is also in non-smooth optimization. And we have developed algorithms that can minimize these kind of problems. And the reason why we have developed this kind of problems is because I wanted to solve this thing exactly. Although it might be not too useful for many applications, but I wanted to find an algorithm that can compute the solution of this thing here in very short time. Okay, so to make things a little bit more abstract, we consider the following class of problems we want to minimize. It's the sum of two functions, f and g. And in the function f, there's an additional linear operator involved. So we can very easily match this thing to our discrete Roth model, f kx g of x. We see g of x is just this thing here. And f of kx is k will be our derivative operator, which here you see it's just linear. So it's a linear operator on the image. And the f function will be this lambda times mixed to 1 norm. So this is a broader model that captures also much more problems. For example, quadratic programming, linear programming, conic programming can all be written in this form. So this is quite a huge class. So we assume that f and g are convex functions. And the main the crucial assumption here is that they can be non-smooth. So they can be absolute function, can be norms, and so on and so on. And as I said, k is a linear continuous operator. So there's no free lunch, so we cannot just assume any type of non-smooth function f and g. What we additionally assume that these functions are simple. Simple non-smooth function. And simple non-smooth function means that we can solve in closed form or with very fast algorithms these optimization problems efficiently. And these are called proximal maps. They're called proximal maps because you're minimizing the functions, but you stay in the proximity of this given point, here p hat or here x hat. Therefore, they're called proximal maps. They can also be seen as a generalization of projections onto convex sets. So a projection onto a convex set, you have a point and you want to project it to the set and minimize the quadratic distance to your original point. And when you say this is the indicator function of a convex set, it's a simple non-smooth convex function, then this is equivalent to a projection. But here it's more general. It is with respect to any convex function here. In many cases, these proximal operators are easy to compute. For example, if this is the L1 norm, it's just a pointwise soft shrinkage. Maybe some of you have already heard about shrinkage functions. If this is a quadratic function, then you just need to solve a linear system of equations. If this is an indicator function of some convex set, then it's just a projection, and so on. So as I said, it turns out that many standard problems can be cast in this type of framework. So the most important brick I need in order to derive primal dual algorithms is the definition of the convex conjugate. Who has ever heard about the convex conjugate? Or Fenchel transform in physics, it's known as Fenchel transform. In mechanics, Fenchel transform you've heard, between Hamiltonian and Lagrange and U. Okay, U. In principle, it's quite an easy thing. You have given a function f of x, any function. You don't have any assumptions on this function. It doesn't have to be convex or lower semi-continuous, nothing. And you define a new function which is the convex conjugate, which is called f star of y, and y is a slope variable. Okay? And it is defined as the supremum of x times y minus f of x. And what you are doing is this first term, x times y, so inner product between x and y. In 1D, it's just x times y. For a fixed slope, y, it's just this line here, x times y. Okay, everyone agrees this is x times y? Yes, I hope. And y is fixed, keep this in mind, this is the slope. And now you would like to find that point x, which should, also, of course, also be in the domain of the function f. So any point here along this line, where this difference between this line and the function is maximized. So supremum, we can think of if the supremum, you know, if a maximum is attained, we can replace this by a maximum. We would like to maximize the distance between this line and f of x. So now when we walk around here, so here the distance, this is lower than this, so it's, let's say, minus 10 plus 5, it's 5. And it turns out that the point where this distance is maximized is exactly in the point where this line is parallel to the tangent of the function. So here we have exactly this guy minus this gives us the maximum distance. Why is this the case? If everything is differentiable, so why should it be the tangent? It's quite easy. If everything is differentiable, we compute the derivative with respect to x. We get y minus, in 1D it's just f prime of x is 0. So you can also say y should be equal to the derivative. Okay, so it's an easy optimization problem. You would like to find the point x where the derivative is equal to the slope, the pre-given slope. And this is exactly this point here. And now this value is exactly, you can read it off from this axis here. So it's exactly this distance from here to here is exactly minus f star. Okay, and now what you're doing is you say I have a new function which for every y computes this. And since this is a pointwise maximum over linear functions, it's per definition a convex function. So f star of y is per definition a convex lower semi-continuous function. It doesn't matter, whatever you input here, f star of y is always a convex function. It's a pointwise supremum over linear, many linear functions. And the funny thing is, once you have done this, and you do this again on this f star function, then you get the f star star function. Then you get the convex envelope of the original functions. In this case, it would be a function that closes this non-convexity here. And in case the function f of x was already a convex lower semi-continuous function, then f star star is again the same function. So by applying this transformation twice, you get back the original function. And if the original function was non-convex, you get the largest convex envelope below the function. So it's a great tool because it means I can solve all non-convex optimization problems. I just need to apply this transform twice. Then I get a convex function. Then I can minimize it. That would be great. The only thing is that computing this thing is not always tractable. So for these non-convex problems where you would like to apply this, usually it turns out you cannot do it. But for some problems, you can do it. Okay, so keep that formula in mind. Now what we are doing is the following. We want to transform this problem based on this convex conjugate. So based on this formula here, we can say that this function f star is the maximum of x times y minus f of x. Or vice versa, we can just exchange here this star with this guy and take the maximum over y. So it's just exchanging the role of the original function and the second function. When we do this, actually, maybe I write this down. I think I'm much too slow. So I start with min x f of kx plus g of x. And now I have the definition that f of kx is the maximum over y of kx times y minus f star of y. So here the variable is called kx. So k doesn't disturb me, just k times x is the variable where I do this transformation here. then I just replace this thing with this part. So I get min x max y kx times y minus f star of y plus g of x. And now I have obtained this kind of problem. And this is a saddle point problem. So you're minimizing in x and maximizing in y. And the good thing here is now this linear operator, which was here in f, and this causes the main problem. Because minimizing this function f with this linear operator inside, this is really the bad thing. Now with this transformation, this linear operator is now in this inner product. And the inner product, it's bilinear. So it's much easier. You can differentiate it with respect to y or k. It's very easy. And instead of having this function f, I have now an f star function. But it turns out that if f is simple, then also f star is simple. So for example, these proximal maps can also be computed for f star easily. There's something called Moreau identity. Maybe you've heard about it already. Okay. And in addition, what I can also do is I can also replace G with this kind of transformations, and then I end up with a pure maximization problem, which is then the dual problem. And everything what I did here is the so-called Rockefeller-Fenchel dual. So this is the original, the primal problem, and this is the dual problem. And there's also a primal dual gap. So you're minimizing the primal, you're maximizing the dual, and everything is convex. There is an optimal point of optimal pair of points, x and y, and where x is a minimizer of the primal problem and y is a maximizer of the dual problem. And in this case, the value of the primal and the dual problems are equivalent, so that the gap is 0. So the difference, this minus this. So you see, this minus is replaced because we're doing a difference. Just gives you this thing here, and this gap vanishes if x and y is a primal dual optimal pair. Okay, so and what we focused on in an algorithm I will now explain is we focused not on a primal or the dual problem. We focused on the intermediate problem, the primal dual problem, where we just have replaced this f function with the convex conjugate, and this is this kind of saddle point problem. And saddle point problem it's not very easy to visualize. I tried to, but this is some, in x and y, some saddle point, and you try to find this guy here, which is the saddle point here, this one here. So when you compute the optimality conditions, the Euler-Lagrange equations, they somehow look like this. So since g and f star are non-differentiable functions, you have to deal with sub-differentials. So this partial g and partial f star, these are the sub-differentials, set valued. And therefore you're looking for points x hat and y hat where 0 is contained in this set valued derivative on the right hand side here. Okay, so the algorithm we are using most of the time, we have proposed in a series of papers together, mainly with Antonin Chambol. It's doing the following. It's very easy actually. We try to find a saddle point. So what we're doing is we make a more or less a gradient descent step in the primal, followed by gradient ascent step in the dual. And you do this until you have converged to a saddle point. There are only a few tweaks you need to respect. For example, here we make a gradient descent with respect to the primal. And here a gradient ascent with respect to the dual. But you cannot take the primal variable from the previous iteration. You need to make a extrapolation based on the new value and the old value. So, and this is important in order to show convergence of the algorithm. If you don't do this, it works in some cases, but not in the pathological cases. Then you need this over-relaxation here. And this is always the gradient descent step with respect to this term here, and followed by an implicit step that involves the proximal map. So the non-smooth term, and this is the reason why this algorithm actually works, the non-smooth term is somehow eaten by this implicit step. And the implicit step is defined by the proximal map, and we have assumed from the beginning that these proximal maps are easy to compute. And here the same, a gradient ascent with respect to this linear term, with this linear combination or extrapolation, followed by a proximal map with respect to the non-smooth term. So here, these T and sigma, tau and sigma, these are in general preconditioning matrices, but you can think of them as just a primal and a dual step size. So in the easiest case, this preconditioning matrix is just a scalar value, and then it's a primal and a dual step size. And in the most general case, this algorithm converges if theta is 1. If theta is 1, it means 2 times xn plus 1 minus xn. And if sigma 1/2 times k times t 1/2 squared is less equal than 1. If tau and sigma are just scalar step sizes, then it means that tau times sigma times the squared norm, operator norm of this linear operator should be less than 1. So in our case, K will be a matrix. We can compute its largest eigenvalue easily, and we can very easily find out what is the primary and dual step sizes that guarantee convergence of the algorithm. As you can see here, tau times sigma is just important, so you can always take a larger tau and a proportionally smaller sigma or vice versa. The good thing about this algorithm is that it gives in any situation an optimal convergence rate. So there exists works that show lower bounds for first order methods for convex optimization. And this means that if you have an algorithm that just exploits derivatives, no second order derivatives, just first order derivatives, you can give bounds that no algorithm that is based on first order derivatives can be faster than a certain convergence rate. So there are lower bounds, they are unbeatable. No algorithm can be faster. For example, for quadratic problems, what do you think, what's the fastest algorithm? What would you use as a first order method for quadratic problems? Conjugate gradient, maybe? CG? Actually, CG is an optimal method. You can show that it's equivalent to the lower bound, so you cannot improve it. And here, this algorithm, this primary dual algorithm, is also optimal in 3 different settings. If both f star and g are non-smooth, then it achieves a convergence rate of 1 over n. N is the number of iterations, so the primary dual gap goes down like 1 over n. And if one of these things are strongly convex, then you can accelerate the algorithm. You get 1 over n squared, which is already much better. And if both f star and g are strongly convex, then you get a linear convergence rate. And these parameters here that are involved show you that actually in any situation this algorithm is an optimal algorithm. And you can only improve on its constants, but not from the asymptotic rate. Sometimes it's hard to choose these step sizes tau and sigma, or these preconditioning matrices, and what we have worked out in one of our papers are simple rules how to choose these step sizes in a plug-and-play fashion. So given a linear operator k, it turns out that you just need to compute row-wise and column-wise norms of the linear operator, take it 1 over, and this gives you step sizes which ensure convergence of the algorithm. So here's some parameter alpha. This is used to vary between pure primary and pure dual preconditioning, but usually I use alpha 1. So it's just 1 over the L1 norm here, 1 over the 1 norm here, column-wise and row-wise, and then you have feasible step sizes. And when you take this choice, put it into this formula, you see that you get a feasible convergence rate. So you don't need to bother with these step sizes. You can compute it in a plug-and-play fashion from your linear operator. Now let's apply this to the Roth model, finally. So in the Roth model, we know that the linear operator is our finite differences operator. The f function is lambda times this mixed to 1 norm, and g is just a quadratic difference. So in the primary dual algorithm, we need the convex conjugate of this mixed to 1 norm. And actually, the convex conjugate of a norm is always the indicator function of the dual norm bar. So it's this delta function, which is 0 if you're inside this set and infinity outside. So it turns out the dual of this function is just a projection in the proximal map. And here you have the dual norm ball, so the 2 via duality stays a 2 and the 1 is turned to infinity. So you always have 1 over p plus 1 over q equals 1, and p is the index of the primal and q is the index of the dual. Then the saddle point problem looks like this. What we need to check is the proximal map with respect to this guy and the proximal map with respect to this guy. So here it's very easy. It's just this formula pointwise. And here we have the indicator function of the 2 ball. So it has radius lambda. So here we see that it has radius lambda. And it means if we're outside, we need to perform an orthogonal projection onto the disk. If we're inside, we can stay inside. And this simple geometric thing is written down with this formula here. So you see, if the length of this point divided by lambda is less than 1, you stay with the point, you divide by 1. And if you're outside, you divide by its length divided by lambda. And then you're exactly at the radius. Very simple. And this is done everything pointwise. So this is the first result with the ROF model. Who knows this guy? It's Charlie Chaplin. It's early days. So this is the original image. This is an image where I artificially added noise, Gaussian noise. IID, so independently identically distributed with some certain standard deviation, and this is the result you get from the ROF model. So see, it works. You can remove the noise. When you should not look too close, then you will see certain block-like structures. But they are coming from the fact that the ROF model likes piecewise constant image, like our bottle, plate, and orange image. So this is the perfect image for the total variation. This is not exactly this kind of image, but it still works. Okay, so the ROF, now I'm talking a little bit about extensions of the ROF model. The ROF model works quite well in case of Gaussian noise, but it performs very bad in case of outlier noise, impulsive noise. Anyone knows salt and pepper noise? You have ever heard about salt and pepper noise? So it is like taking an image, putting salt and pepper on it, which means that randomly some pixels are set to white and some pixels are set to black. Salt is white, black is pepper, obviously. And in this case, the noise is not Gaussian distributed. It's more impulsive or outlier noise. And it turns out that the so-called TVL1 model is much better in this case. And it just means that the quadratic distance here is replaced with L1 norm. And the L1 norm, it's more robust because of its linear growth to outliers, and therefore it works much better. This is also a very nice model from a geometric point of view. For example, it's contrast invariant. Contrast variant means if you solve this problem for a certain u, then you for a certain f, and then you replace f with c times f, then the solution is exactly c times u. So you can, once you have solved for f, and for any family of c times f, you can solve it by just taking c times u from the previous solution. And therefore it has some morphological property. It means it can be used for scale selection. And this is on the next slide. Here's just a comparison. This is an image with salt and pepper noise. You see black and white random pixels. And this is when you start minimizing it with the ROF model, you see there are still many outliers here, but the structures get lost, and the TVL1 model works much better. So it gives a better result here. Obviously, it works not perfectly. It destroys the small scale structures, but given this high amount of noise, it's somehow natural. Later, we will see another method that can denoise this kind of images much better. This is this scale selection. This is sometimes I show this online in my lectures. It's like magic. So when you have this image here, and you start to increase the regularization parameter, decrease. Okay, this is, take this 1 over. We increase it. because it's a different model where lambda is here on the other side, but it doesn't matter. And it turns out that by increasing the regularization parameter, the disks start to disappear. You can remove the disk like magic by regularizing more and more and more. And since it's contrast invariant, the disks removed are independent of the gray value. So the small contrast disk like this one is removed at the same time as the high contrast disk here. So having higher and higher lambda values, they remove. So it means you can remove small scale structures from an image. So if I have an image with small scale structures, taking the TVL1 model, these structures go away. On the other hand, when I use the same thing with the ROF model, you see that the structures with the low contrast are removed first, and these high contrast structures stay much longer in the image. So you get this kind of results then. And here you see the property of the minimal surface, this cartenoid. Look, if you have these two guys here, it starts to produce artificial boundaries that minimize the surface area. So this can already be observed here. Okay, so what in case we have neither Gaussian noise, additive Gaussian noise, or impulse noise, we have some multiplicative noise. If we deal with synthetic aperture radar images, or if we deal with ultrasound images that contain speckle noise or some type of multiplicative noise, then obviously these previous models fail because they don't respect the correct noise model. And therefore it's much better to consider a noise model in this multiplicative noise, in this multiplicative form. You say that your noisy image is the clean image times some noise component, which has mean 1, and usually modeled as a gamma or Poisson distribution. And in such cases, it turns out that a TV regularized model with an entropy type data term performs much better. So the data term now looks like this. So it's u minus f times log u. And this is the negative entropy. And the negative entropy is also a convex function. So it somehow looks like this. Also, the proximal map with respect to this data fidelity term is very easy to solve. You just need to solve pointwise a quadratic equation. It's very easy. And here's an example. Here's an original image. Here is a noisy image with some multiplicative noise. This is when I use the ROF model with the quadratic data fidelity term. You see a lot of these fine scale structures, like these trees here, are lost. And with the entropy data fidelity term, you can keep much more structures here. So the data likelihood distribution should also match the noise, of course. So if it doesn't match, then we can expect that we get worse results. What about image segmentation? So in image segmentation, so once you, when you have ever used PowerPoint, then there's some tool where you can remove the foreground, right? Maybe many of you have already seen this. You can remove a face or a person in PowerPoint. And something very similar we can do also with the total variation. Namely, assume we have given an image with some foreground object and some background object. And let's assume this is a color image. And by just for example, fitting a probabilistic model to the foreground and background, like a histogram to the color values or a Gaussian mixture model to the color values, we can get some probabilities of the image given foreground and given background, so which somehow describe the color distributions. For example, if the background is green, then there would be a probabilistic model which is more in the green area. If the foreground is blue, then it will be more in the blue area and so on. So when we consider the negative log ratio function, so which is the ratio between these two probabilistic models for a certain pixel x and taking the negative logarithm, so what do we see? If it is more likely to be a foreground, we get a number larger than 1, so the negative logarithm will be negative. And if the foreground, if it's more likely to be a background, we will get here inside something smaller than 1. and therefore the negative logarithm will be positive. So this W will be negative, it is more likely to be foreground, and positive if it is more likely to be background. And it's now we can consider the following model. We say that our image we would like to optimize should be a segmentation, so it should be binary image. So each image pixel should be 0 or 1. And we minimize the total variation, because we know this leads to compact shapes. Of binary images, it's exactly the perimeter of the segmentation. And additionally, we have U times W. So if W is negative, U would like to be 1, because we minimize, so it gives a negative contribution, and if W is positive, U would be 0. So U switches between 0 and 1, depending on the sign of W, and also of the value, because then it switches more likely. So therefore, the model tries to minimize the trade-off between the boundary length of the segmentation and partitions the image into a foreground region where U of x is 1 and background region where U of x is 0. So this I have already explained. For a pixel where the probability of the foreground is larger than the probability of background, W will be negative, and if it is vice versa, then W will be positive. And something that is still disturbing us here is this condition that the image pixel should be binary, either 0 or 1. But then it turns out that actually we can make use of the ROF model to solve exactly this problem. So this is work of Chambol in 2005, and also Benjamin did some work with a slightly different model, but actually based on a similar idea. Is the following: you take the W function, which is this log ratio, as a noisy image. You consider it as a noisy image. You apply the ROF model, denoise this function, and then you threshold it at 0. And thresholding at 0 gives you a foreground and a background region. And this is exactly the thresholding operation, this foreground-background region, then exactly gives you the minimizer of this problem here. It's quite interesting. If you're interested in this, you should consult this paper here. So it's quite geometrically involved, using these level sets and thresholding formulas and so on. So therefore we see, although this ROF model for image denoising, it's not very useful, but it can be used as a brick to solve more interesting optimization problem like this image segmentation problem. And since we have already a fast algorithm to solve this problem here, this primary rule method, we can also do image segmentation with the same algorithm. Here's an example. Here the user has just marked this should be foreground and this should be background. Based on that, I've implemented a Gaussian mixture model that describes the color distribution of background and foreground. And then I make this log ratio test, which gives me this function. You see negative dark values correspond to foreground and brighter values correspond to foreground. And then I just denoising this thing here and threshold it at 0, and the threshold then looks like this. And when you overlay this binary mask with this object here, you have exactly extracted the object. Image inpainting. Image inpainting is more or less an image processing task where you try to get back or invent lost image information. For example, if your image looks like this, here it's bright, here it's dark, and there's a region where the image content is lost, you as a human would say, clearly, I need to connect this line, then I have repaired my image. So you want to repair your image, you want to get back information about your image. And since the total variation is a reasonable model for images, we can say, okay, let's try how well the total variation works for image inpainting. Mathematically, it means we want to minimize the total variation in our image, subject to some boundary conditions that in some regions where the image is not lost, U should be equal to the given image F. And this is an example. This is the original image. Here, only 5% of the image pixels are known. 95% are lost. And using this model, you can get back this image here. Actually, it's not a good result, so it's not state-of-the-art. We will later see that with better models, we can get much better results here. But still, somehow reasonable. The big objects, like the leaves here, they can be found. Of course, smaller things like here, they are lost. But from 5% of the pixels, it's a little bit hard to get these guys.
How do you decide on which pixels to lose?
Randomly. You can do this randomly. This is just, for illustration. It's not a real-world problem. Image deblurring. The ROF model can also be modified such that it can be used for image deblurring. This relates to the fact that we have a linear operator in our data fidelity term. Here the linear operator is just a convolution with a Gaussian blur kernel or with a motion blur kernel. So if your camera, while you took the image, you move the camera, then you get this kind of motion blur kernel, and then you try to find an image U that again has low total variation, and when you blur the image, it should give you the original blurry image. And this works quite well, as you see. Original image, here the blur kernel is this one with the camera, then you get, this is your observation, and then by minimizing the total variation, you get back this image here. The reason why it works is because this has less edges. Only a few strong edges, but not edges everywhere. And the blurry image has edges everywhere. So the total variation moves you to the right image. If you don't use regularization, just try to invert this thing here. Then it's, of course, ill-posed. Then you get very noisy results. And finally, maybe before we are doing the break, then I need to accelerate a little bit. MRI reconstruction, I already mentioned it. As I said, in the MRI reconstruction, the measurements that they are taking in the Fourier domain. And how does it work? So the hydrogen nuclei emit a detectable radio frequency after applying high frequency pulse. So you first have a strong magnetic field, static field. Then you apply a high frequency pulse, and then the spins are changed, and they then emit a detectable radio frequency. And this radio frequency, which is then recorded by so-called receiver coils, they are measurements taking the Fourier domain. And with each high frequency pulse, you can get one line in the Fourier domain. And once you have taken enough lines, you can apply the inverse Fourier transform, and you get your image. So there's one issue. Since we always have to wait after applying the high frequency pulse, after the molecules have aligned again with the static magnetic field, you need a lot of time. So therefore, for a 256 squared image, it takes approximately 4 minutes. Everyone that has already been in an MRI scanner knows that it takes a lot of time, and it's a strong noise where you hear that this high frequency pulse is applied. And it would be great, of course, to speed up this procedure. Physically, there's a limit. You cannot. But what you can try is you can try to take fewer measurements in the Fourier domain. Additionally, in state-of-the-art MRI scanners, they have so-called parallel MRIs. They have multiple receiver coils. So you have many receiver coils recording the signals from different positions. For example, this receiver coil is more sensitive in this area. This is more sensitive in this area, and so on. So you can get better and more measurements in the same time. And from a mathematical point of view, how is this modeled? It's again a least squares data fidelity term. A is now a combination of the Fourier transform and these sensitivities from the different receiver coils. So you first have to weight your reconstructed image with these sensitivities, and then you can apply the Fourier transform. And outside, there's also a sparsity pattern that tells you which of these lines you have actually recorded. Because if you want to accelerate this MRI acquisition, then you would like to spare out a few of these lines. In summary, a total variation-based reconstruction model looks like this. You take this as a data fidelity term. So you see U times C gives the weighted images. Fourier transform then should correspond to your measurements. And the total variation takes care that we get rid of the noise and backfolding artifacts. And this is how it looks like. This is if you would not apply regularization, you would get images like this. And with the total variation regularization, you get much better images. But still, we will see later, based on learning, we can get much, much better results. But also for the learned model, the structure will be quite similar. So it will be just that we will replace the total variation by a learned regularizer, which is much more expressible. Okay. Last slide before the break. Some shortcomings of the total variation. In the very beginning, we have developed a model saying that we have an image which is piecewise constant. It was the plate, the bottle, and the orange. Piecewise constant images. And therefore, the total variation actually tries to make every image piecewise constant. This looks piecewise constant, right? So it has a tendency to produce piecewise constant solutions. This is particularly bad if your image is smooth. For example, a linear gray value ramp like this one here. So therefore, when you take a noisy version of this one and denoise it with the ROF model, you see these block artifacts. And when you draw the graph of this function here, you see that it's like many, many small staircases. And therefore, this effect of the ROF model is known as the staircasing effect. And after the break, I will show you how you can get rid of the staircasing effect. Okay. So, okay. Welcome back. We stopped at the staircasing effect of the total variation. And now we will discuss two choices how to get rid of the staircasing effect. So the first is a more engineered approach, which is based on the simple fact that the 2 norm here, x, norm of x, is replaced by a smoothed norm. And this means simply, so if x is just 1D, then the 1 norm and the 2 norm are equivalent. You replace it by replacing this lower kink with a quadratic function. This is the standard Huber function. So it is quadratic if absolute x or 2 norm of x is less equal than epsilon, and the 2 norm else. So that's, and with this, it turns out that you can already get better results. You see these blocking artifacts are somehow vanished, but on the other hand, you also see a kind of noise pattern in the face of the person. So it's not perfect, but in many applications, this is sufficient. It also makes the optimization a bit easier. And the second one is a concept based on a generalization of the total variation to higher order derivatives, which we have developed some years ago. And this is known as total generalized variation, abbreviated TGV, according to a fast French train. And the basic idea is that the concept of infimal convolution is also a very nice concept of convex analysis, where you say that I have two functionals, one, for example, penalizing first-order derivatives, the second one penalizing second-order derivatives, and I'm minimizing over u, which is the sum of these two guys. And these two functionals can decide which part of u goes into the first-order penalization and which part of it goes into the second-order penalization. So in case of non-homogeneous functions like these semi-norms, it turns out that this infimal convolution is the convex relaxation of the minimum of the two functionals. So it means this partition into u1 and u2 is pointwise selected such that the minimum of these two functionals is penalized. And a very similar concept, slightly different, we have introduced now almost 8 years ago, together with Christian Predis and Karl Kunisch. And if you still remember the definition of the total variation, so it was this u times diff of phi. And the only thing what we now did is that we say, okay, phi is not a vector field, but it's a tensor field. And we take the Carth order divergence. Okay, so if you have a tensor field and every time you take the divergence, it gets from a tensor to a matrix to a vector and so on. So the divergence operator reduces, of course, the dimension. So we take the kth order divergence, and additionally we also have that the lth order divergence of phi should satisfy these pointwise constraints, and L is going from 0 to k minus 1. For example, if you take k equals to 1, then it's just the divergence, and L goes just from 0 to 0, because k is 1, and then it's just the 0 order divergence, which just removes divergence, and it's a pointwise restriction, then we end up with the total variation. So for k equals 1, this definition is equivalent to the total variation, and for k larger than 1, you get second order, third order, fourth order TGV, and so on. Something is also important to note, that this thing here is equivalent to this definition in 1D. If you have just signals, not images but signals, then those two definitions are equivalent. So let us consider the case where k equals 2 for images, because you can get a better intuitive understanding how this thing works for k equals 2. Using duality concepts, so based on the fancy conjugate, you have to write down a little bit, but in the end you end up with this regularizer, and it works as follows. For example, if v equals 0, this term vanishes, and you end up just with the total variation. But you see, before you are taking du, you subtract a vector field v, which is an auxiliary vector field, and if this vector field itself has a low total variation, then it is more cheaper for this functional. And this vector field captures the slanted areas of the image, so where there's a constant increase or decrease of intensity values. And therefore, this functional can be used to reconstruct piecewise affine functions. So in an affine region, the gradient is constant. If it's affine, the gradient is constant, but this constant gradient can be well modeled by vector field v, which is piecewise constant, because the slope is in a certain region constant. And therefore, in affine regions, this model tries to approximate the gradient with this auxiliary vector field v here. And if you have a jump, then it can still allow for jumps as the total variation. So this model somehow combines, in a convex way, a sort of a model selection. If locally the image looks like an affine image, it approximates it with this affine part. If it locally looks like a jump, then it approximates it with this jump part here. So it undertakes a model selection based on how the image looks like locally. Okay, in order to discretize this guy here, in this case for image denoising, we take exactly the same what we have already developed. The gradient operator here is replaced with this finite differences operator. V is an auxiliary vector field, and this bold font D matrix is nothing else than a combination of two of these finite differences operator we have already developed. So the discretization is very much in the same spirit as for the total variation. It's just that we now have a slightly more complicated functional to minimize, but this is a norm, linear operator, quadratic norm, it's convex, can be cast into this framework of primal dual algorithms, and we can minimize it. So here just a few more details about how these mixed 2-1 norms look like, but there's no surprise. You take component-wise the 2 norm, sum it up. Here component-wise the 2 norm. Now on these more components and sum it up. The saddle point formulation looks like this. Looks complicated, but once you have understood the concept behind it, it's more or less plug and play. Now let's get back to this test image. This was the result for the total variation-based denoising with this blocking artifact. And now as a comparison, you see with the total generalized variation, we can almost perfectly reconstruct this piecewise affine image. There's a small rounding effect at jumps, because it turns out you can save a little bit energy on the jump by making it a little bit smaller, by making slightly flatter slopes around the jump. But this is due to the convexity of the model. We tried to get rid of that, but we didn't really find a solution to this problem. Okay, so how well does it work for image denoising? Original image, you see it's well selected from myself because it has a very nice affine part in the background. So we expect that the total generalized variation should work very well here, and indeed the TV makes lots of staircases in this affine part, and the TGV can nicely approximate this smooth part here. I have to admit that actually for image denoising, when you really make a hard evaluation how well it works, you don't get better results with the TGV. But it turns out for images which are piecewise affine, like depth images, disparity maps, and so on, I will show later, this is really a very good model. But images are also not very well modeled by piecewise affine functions. It's more that the geometry of the 3D world can be well approximated with piecewise affine functions. And therefore, what we did already a few years ago, you see 2011, together with a PhD student who is now working at Amazon Prime Air, where they do strange stuff with drones. They are not allowed to talk about it, but you can imagine what they are doing with drones. This time back, he was working at Microsoft Photogrammetry. There was a company from Microsoft in Graz, and they were doing digital 3D models of cities. And one problem was that they had very noisy depth maps. So here you see that the intensity value tells you how far a certain image pixel was away from the camera. And in this case, it was aerial image, so a plane was flying over the city. This is a church in Graz. And the intensity value measures the distance from the plane to the object. Brighter means it's higher, and dark means it's lower. And the plane was flying over Graz, and it were taking a lot of images, and always from 2 pairs of images or triples of images, they were able to compute depth images by simple triangulation. And this gave them a lot of these noisy depth maps, and now the idea was, can I compute a nice depth map by jointly denoising all these noisy maps here? So some are combining all these noisy maps and do a joint denoising, and we came up with this following formulation here. And since geometry can be well modeled with piecewise affine functions, you see a roof is nicely affine, the road is affine, and cars can be well approximated. Maybe not trees. Trees are not so well approximated, but trees are not so important. But man-made structures, buildings are well approximated with affine functions. We came up with the idea that we penalize, we are looking for a noise-free depth map U, which we penalize with this total generalized variation of second order, because it favors piecewise affine solutions. And we say that U should, we penalize the L1 norm between this solution U and all these different disparity maps. So DI is first map, second, fourth, until, I don't know, 10 different maps we had. So I goes from 1 to, say, 10. And it turns out that this is very nice and cheap to optimize. We can cast it as a primal dual formulation. And it also turns out that the proximal map with respect to the sum of the L1 norms is easy to evaluate. There's a nice paper of Lee and Osher where they show whatever you need to do is you need to get some values, you sort them and take the median. And this is the solution of the proximal map. So you just need to solve small sorting problems, very efficient, n log n time. And this is the result we got then. So this is a result of these disparity maps, and this is the denoised disparity map. Yeah?
Can you go one slide back, please?
Yeah.
This minimization, this is just the denoising, right?
Yes.
So, but there's another part to this optimization, right?
No. You mean this?
So how do you get this three-dimensional structure?
What do you mean? This additional optimization in V, or what do you mean?
No, so in this particular problem, I mean, what you want is
No, you want an image.
this three-dimensional.
Yeah, but the image is just a height image. So if you take this image and elevate each point and triangulate it, then you get this 3D model. So when you consider the graph of this image, you get this church. Okay, you have an image for each pixel, you have a height value. And now you get for each pixel a height value, and you triangulate the surface, then you get exactly this thing here.
So you have different depth maps from different positions?
Yes, they are all warped to the same position. So this is what we are doing here. I didn't give you the details here, but you know, you have one object, you're looking from here, you're looking from there, you're looking from slightly above, from slightly below, and then you all project everything to the same coordinate system, and then you get many different disparity or depth maps. Yes, this is done beforehand, but this is easy. This is structure from motion. This is just a translation and rotation of the camera. This is not difficult. Just a few parameters. Okay, clear? And this is the denoised disparity or depth map. So when I speak about depth maps or disparity maps is when you take your two eyes and you're switching between left and right, you see that the objects are moving. And if the objects are closer, then they're moving more, and if they're further away, they're moving less, right? So everyone knows this. And this distance shift of the moving of the object, this is called the disparity. And when you take 1 over the disparity with some scaling factors, you get the distance from the object to your eye. So the disparity and the depth maps are 1 over indirectly proportional. But here, these were really depth values, and so you can easily draw the 3D object then. And you see there's a roof, there are small thin towers and chimneys, and the total generalized variation is really a good model for this kind of 3D structures. And when you put texture on this model, you can get these nice images then. So far we haven't talked about color images. So all images we have considered so far are just scalar images. It means we have just a scalar intensity value. But when you talk about RGB color images, of course, each pixel has a 3-dimensional vector. There are red, green, and blue color values, or you can have other vectorial images. So the question is therefore, what is a good generalization of the total variation to vector-valued images? And in principle, you could use any matrix norm acting on the Jacobian du. So now it's not a gradient, it's a Jacobian, because u is a vector, and you get the derivative of each component of the vector, which is a Jacobian. And an interesting class of matrix norms is given by Hutton Norms. And the Hutton Norms are norms that are operating on the singular values of the matrix. So I guess many of you know this kind of Hutton Norms. If you have the 2 Hutton norm, then it's equivalent to the Frobenius norm. If you have the infinity Hutton norm, then it's equivalent to the operator norm, the largest eigenvalue. And if you have the 1 Hutton norm, then it's just the nuclear norm. That means this just the sum of the singular values. So these are the formulas. You see, you take the LP norm on the singular values. And the infinity norm is the maximum of the singular values. The largest singular value is related to the operator norm. So it means we can just consider vectorial images here, now in bold font, vectorial noisy images, and take these Jacobian finite differences, which just means we apply our usual finite difference operator to each component and bring the corresponding derivatives together and take then the Hutton norm pointwise. Primal Dur, everything standard, same as before. And the question is, how can we do the proximal mapping now with respect to the dual Hutton norm that is involved in this conjugate function? Then it turns out that you just need to perform a single value decomposition of the matrix. And the matrix is small. It's just 2 times 3. You have 2 derivatives, x and y, and 3 components, RGB. So it's a 2 times 3 matrix. Singular value decomposition, and perform just a projection or shrinkage depending on this norm on the singular values. So there's a proof in this paper that this is the correct projection. And here's a small comparison. Original image, noisy image, and this is when you take the Frobenius norm, and this is when you take the nuclear norm. So this means the L2 norm on the singular values, and this means the L1 norm on the singular values. And you see that you get slightly more structure, but it's very subtle differences only here. It's just to mention that you can easily extend this to color images. Other analysis operators. So everything we have discussed so far is based on just taking differences between neighboring image pixels, finite differences operators. The question is why not taking a different linear operator acting on an image, for example, a wavelet decomposition or shearlet, ridgelet, curvelets, XXXlets, whatever you would like to have. And in principle, you can take any of operators. Some work better, some work worse. Something that works quite well is the so-called shearlets, because they can be shown to provide optimal sparse approximations of cartoon-like images. So they are very well in representing a smooth boundary of objects. And then the corresponding variational approach looks like this. Here you have this operator, and the shearlet is very similar to a wavelet. It performs a decomposition on different levels, but it's a complete linear operator, and also the inverse operator is quite easy to evaluate, and you can then perform this minimization here. So here's an example for inpainting, and now we see that actually the total variation is not very good for inpainting. This is the original image. Here I'm missing 10%, sorry, I'm missing 90% of the data. This is inpainting with total variation. It just gets back the main parts, but it works much, much better with a better linear operator like the shearlet transform. Because the shearlet transform, it somehow can capture these small line structures and gets better outlines of the shapes here and works much better. It's of course much more costly to minimize this because this operator is much larger. Finite differences is really very, very efficient, but this has multiple hierarchies and so on as a wavelet transform. Just to mention that we can easily extend this idea of sparsity in some transform, where the total variation is sparsity in the gradient transform, to a sparsity in another transform, which is more suitable for images. Something I would also like to mention is that we can also do synthesis of images. Everything we have done so far is we considered analysis operators. Analysis operators means that we have an image and there's an operator which analyzes the image. And based on this analysis of the image, we penalize the L1 norm of the coefficients. The other point of view is the following, that we say that we have a sort of a dictionary of small atoms, and we want to construct the complete image by, taking part of this dictionary. For example, an object, it's like solving a puzzle for an image. So these are your parts of your puzzle, and you put these puzzles together and to get the image. And the restriction is that each part of this puzzle should be used only a few times. Sparsity in the usage of the puzzles. And you can scale the value of this puzzle. So there's a coefficient which you can multiply each entry of the dictionary to add up your image. So this is a class of problems, so-called synthesis operators, which dates back to the work of Aharon, Ellert, Bruchstein, 2006. And the learning of these puzzle parts for an image like this can be done with the classical lasso problem. This is a problem coming from statistics. Here you have patches which you have extracted. You extract all patches, and you say, I would like to approximate my patches with this dictionary times coefficients, and I penalize the L1 norm of the coefficients because I want to find a dictionary that is very universal, so that only have to use part of the dictionary to approximate the patch. One problem here in this approach is that it is working on each patch independently. So it's really in the space of patches, and once you have solved for the patches, then you need to add them up together to form the image. And therefore another model, which at least I think it's more suitable for images, is the so-called convolutional lasso. And this is quite an interesting model. Here say again you have your noisy image F, or your original image F, and you say I have certain coefficient images Vi, and when I convolve these coefficient images with these convolution kernels and add them up, then I should be able to approximate my original image. So for example, if the convolution image has just one delta peak and I'm convolving the delta peak with this structure, I'm getting a small piece of an edge. And if I have a line and I'm convolving this line with this patch, I get a certain part of the object. And additionally, such that I get a sparse representation, I also require that the L1 norm of this coefficient image is small. And what you see here is that I minimized this problem both with respect to the coefficient images and with respect to the dictionary. And in order to make the problem useful, the dictionary has to be constrained, for example, to have a 1 norm less equal than 1 and so, or 0 mean. And then you actually find this dictionary that is the basis, more or less, of this image here. But this is a different point of view here. I'm doing a synthesis. So I have a dictionary and I want to build up, based on this puzzle of parts, my image. And the other approach we have taken before was I'm analyzing my image with an operator. Okay, so now let's come to a typical computer vision application, which is the computation or estimation of motion of image sequences. So it's quite an important task. When you as a human, if you're moving, you're doing optical flow estimation all the time. So if something starts to hit you, you detect the motion and you know that it's coming to your face, and then you try to circumvent it. This is needed for autonomous driving to detect if some pedestrians are crossing. This is necessary for robot navigation, and so on and so on. So optical flow is really one of the very fundamental problems. So it's also called the apparent motion in image sequences. Optical flow is a vector field, as visualized here, that describes the motion of intensity values. Okay? So you see the intensity values are moving from the first image to the second image, and you would like to know for each pixel with a small arrow where this pixel has moved in the second image. And it's important to note that this is not a real 3D motion, so it's not really the 3D motion of the object, it's just a projected motion onto the image plane. And in order to visualize these arrows in the community, certain color codes are used. For example, of the Middlebury, it's a university that has established a benchmark to test optical flow algorithms. They use this color coding here. So you see, for example, moving down like this arm here gives you this color here, and the face is moving, the head is moving a little bit up, gives you this color here, and so on. So each arrow is assigned to a certain color value. So this image is to make you transfer some money to my bank account after this lecture. No, it should visualize that. I mean, it depends a little bit how far you're away, but if you see this image in front of a screen, you really get crazy, because it tells you that strong gradients really cause some kind of optical flow in your brain. So it's really funny to see this. One of the fundamental assumptions in optical flow is the so-called brightness constancy assumption. So what you're assuming is that when an object is moving, the intensity of the object, intensity pattern of the object stays the same. So here this, I don't know if maybe this is an apple or whatever, a tomato, whatever. When you look at this patch here, you see this patch is moving because the hand was moving, but actually the patch looks like the same. It just appears at a different part of the image. Mathematically, it means that if you consider your image sequence as a space-time intensity function, so it's I of x and t, it means if you shift the position by a delta x and the time by delta t, the intensity should be the same. So in the space-time volume, it moves spatially but also in time, but the value of the intensity is the same. It's the so-called brightness constancy assumption. And this is the very basis of optical flow algorithm. So here x is the pixel position and delta x is a small displacement. One problem here is that actually we are interested in delta x, or delta x divided by delta t. But you see, it appears inside the image intensity function, and the image intensity function can be an arbitrary verse function. So, and in order to make computations, what we're doing is, the tool we are using all the time, we are linearizing whatever is nonlinear. So, if you understand linearization with Taylor, then you understand almost everything of science. So, therefore, what we're doing is, assume we have given some initial flow field or shift displacement, u0. We are linearizing this optical flow constraint around a certain position. So you replace your strange function here with a linear function. Of course, we have to take care because this linearization is usually valid only for very small shifts. And therefore, what we are doing is the following. So let's consider this equation here, I of x plus delta x and t plus delta t equals I of x of t. So that's our main assumption. We're assuming the intensity value stays the same. And what we're now doing, assuming that delta x and delta t are small, we can replace this term with a first order Taylor expansion. We say that I of x plus delta x t plus delta t approximate I of x and t plus nabla especially I of x and t times delta x plus, and now the time derivative of x and t times delta t. Okay, and per definition, this should be equal to I of x and t. So this part was this first part. This should be, per definition, be equivalent to I of x and t. Now you can cancel this guy. Then we get that nabla x I of x and t delta x plus nabla t I of x and t delta t equals 0. Then you divide by delta t and delta x over delta t plus nabla t I of x and t equals 0. And delta x over delta t is what? The velocity. And this velocity is called u. And this is the so-called optical flow constraint, which I've just derived. So the spatial gradient times velocity plus time derivative should vanish. So there's one problem. This is when we just consider one point. This is a two-dimensional vector, but we just have one equation. So it's an unconstrained problem. And this comes from the fact that we can detect motion only in direction of the gradient. So if you have an edge, a moving edge, you can only determine the motion perpendicular to the edge, but not in direction of the edge. So if you look through a very small aperture, oops. So if this edge is moving and you look through a small hole, you cannot detect at the same time if the edge is moving like here and at the same time also moving in this direction. We can only detect if an edge is moving in the direction perpendicular to the edge. The only thing where you can detect both things is if you consider a corner. So if you look at the corner, actually then you see if the thing is not only moving this but also in this direction. But of course you cannot see a corner point-wise. In a point you can just see an edge direction, and therefore it means you would need to consider a larger neighborhood of image gradient in order to get a reasonable information about the flow. Mathematically, you see this is an underdetermined system here. Okay. So in practice, we will not be able to assume that delta x and delta t are small. So if we have only sub-pixel shifts, we either have a high-speed camera where we have really very small motion. But in practice, like in this beginning, you see this object is moving by 20 pixels or so. So our assumption that delta x and delta t are small is not really true. So therefore, what you're doing, you make use of a concept of image warping. And the concept of image warping means that you have given some rough estimate of a flow field, U0, and you make a geometric transformation of this image space-time volume based on this initial flow field. So you pre-registering your flow field based on this initial flow field such that the remaining shifts are small. And practically, it will mean that we will start on a image pyramid where the displacements are small. If you have tiny images, also the displacements are tiny, and you will make an algorithm based on a cost to fine concept on the image pyramid, and you will use the flow field from the coarser level of the pyramid as an initialization for the finer level. But I will show this later. So and together with image warping, now the point of linearization is U0, and now our U here is replaced with Ux minus U0 here, and this is with respect to the pre-warped image space-time volume. Okay, so we are already in the shape to define a variational model for optical flow computation. When we go back here, we see this looks pretty much like piecewise constant or piecewise affine flow fields. Let's start with piecewise constant. Therefore, the total variation is already a good regularizer for flow fields. Okay, so I think that's reasonable. Look here, piecewise constant vectors. Here they are almost constant. And therefore, a reasonable model is to penalize the total variation of this vectorial flow field. We have, yeah?
I've got a question regarding the assumptions you made.
Yeah.
That you said we assume the local intensities to be kind of constant for
yes.
the image. But I can think of a lot of different...
Comes later. Of course, this assumption is wrong, of course, but I will tell you ways to get rid of that. Yeah. Okay, so you have a TV regularizer on this vectorial flow field, vectorial total variation, any kind you would like. And in the data fidelity term, we are now penalizing deviations from the optical flow constraint. You see, this is exactly the optical flow constraint we have developed here. Okay? So it means we try to find the U which satisfies the optical flow constraint to 0. It can have some outliers, therefore we are using a one norm. For example, if there's an occlusion, then actually there is no correspondence. Some parts are hidden, so there will be some outliers here. And additionally, it should be smooth. And of course, this can be made better by replacing TV by TGV or any other kind of regularizer you would like to have. So what about discretizing the optical flow field? We already know how to discretize the total variation. We find the differences, but what about these operators here? So in practice, we are usually given two images of an image sequence, first image and second image, and we say I1 is intensity function at x and t, and I2 is intensity function at x and t plus delta t, by moving by delta t. And additionally, we have given a initial flow field that can be used to warp the second image. So we define this I2 tilde, which is I2 of x plus U0 of x and t, so the pre-warped image. Then we can define the time derivative simply by taking the central differences of the second warped image and the first image divided by delta t. And in addition, we would like to approximate the image gradient. And the image gradient should live at the same position when you do this averaging as the time difference. And therefore, we're taking central differences on the first image, take central differences in the second image and average them, because then they also live in between the frames at t plus delta t over 2 at the same position in time where these differences here live. So maybe this is a bit too fast now, but if you're interested in that, I can show you more details, give you more details why this is reasonable. So therefore, the discrete T-well-1 model is already ready. Total variation with finite differences, vectorial. This is the optical flow constraint with these discretizations here. And this can be, again, rewritten as a primal dual saddle point problem, which we can solve with the primal dual algorithm. And it turns out that also the proximal map with respect to this optical flow constraint with the L1 norm can be solved quite easily with a bit more complicated thresholding formula. But this is just distinguishing three cases. Everything is pixel-wise, so you can easily implement it and parallelize it even. I already told you about this, image pyramid. Because we also want to get larger displacements, we need to implement or everything in a cost of fine setting. So it means we first make an image pyramid of our input images, then we compute the optical flow on the very coarse resolution. Then we multiply it by a certain factor and prolongate it to the next final grid, solve it again, take here the solution of this one as an initial flow field here, and so on until we have arrived at the finest level of the pyramid. This works to some extent quite well, but it has the problem of large motion of small objects. So there's an inherent problem. If there is a small bug that crosses the image with high speed, then it is lost on the coarsest level, so that the initial flow field can never be computed. And when it is seen in a final level, then you don't have the right initial flow field so that you can recover the correct flow. So there are some problems with this cost of fine here. So here's an example. This is a classical image pair of the Middlebury benchmark database. It's called rubber whale, because this is a whale which we can use as a rubber. I dealt a lot of that in my PhD thesis because that's the reason why I know exactly the name of these sequences. This is how the ground truth flow field looks like, which they have computed with some technology. And this is how the result of the T-well-1 flow looks like. So you see it works quite well. Of course, you have some problems here and there with occlusions or parts which are very dark, but more or less it works quite well. So I was always surprised how well this simple model works for optical flow, and we also did a implementation on a graphics cards which runs highly parallel, and we even sold this algorithm to many companies, and they're using it and they're quite happy with that. So Manuel Werlberger was one of my PhD students who worked on optical flow, and he generated this video here. And as I said, it works in real time, so there's a moving camera and you're computing the optical flow between two successive frames of the camera, and you see that it works quite well. You can take different regularizations, so more regularization gives you smoother results with coarse outlines. Then if you have less regularization, then you see it becomes noisier and noisier. And you can download this code for free. You can use it, install it on your laptop. It works with the webcam in real time if you have a graphics card on your laptop. Some of the applications he did is to do frame interpolation. So here you see the original frames. Okay. And of course, if you know the flow from one frame to the next frame, you can warp one image according to the flow and make much better resolution in time of the video. Okay, so now we are coming to your question. What about the brightness constancy assumption? So usually there's an ambiguity between the illumination has changed or the object has moved. So what about here? Is this a colored sphere which has rotated, or just the illumination has changed from here to here? No one knows. How should the algorithm know? So me as a human, I would say, okay, the illumination has changed, but this is a much more complicated problem. Saying, okay, here the illumination is coming from here, and now it's coming from here. So it's much more complicated. But the optical flow algorithm, it's stupid. It only sees the optical flow constraint and tries to get piecewise constant flow field. So how should the algorithm understand this? Another problem is, for example, we have been working together with a company that is restoring ancient movies. So, and very often you see the movie is moving, because the scanning of the film, it was not very accurate, and they wanted to get rid of this motion. But at the same time, you see the intensities changed a lot. So in the optical flow constraint gets crazy if the intensity changes, because it assumes that they should stay the same. And I'm now giving you two solutions to this problem. One is a very cheap solution. The solution is you take the original image, you apply total variation denoising, you get this image, and then you subtract this guy from this. And what the difference is, it's the texture. Okay, and the texture looks like this. So this plus this is this, but in the texture, these intensity changes are not contained. And the solution is that you just run the optical flow algorithm on these images then. So you do it on the texture part rather than on the structure part. Because you assume that lighting changes, they are kept in this part here. And it turns out that the total variation ROF model or similar works very well for that. Then this is the, let's say, the hands-on solution. But you can also do a better mathematical model. And the mathematical model, which also works very well, is the following. You take the optical flow constraint, these first two terms. Then you say, okay, when I add an additional function v times a parameter beta, then it should vanish. And what you assume is that this beta times v captures the intensity changes, shadows, for example. And in addition, you also assume that this v function here should be smooth. Okay? Because if you have a shadow in your image, then the shadow is not just points, but is a complete region where there's a shadow. And this leads to this modified illumination adaptive T-1 optical flow. Now you penalize the total variation of both the flow field and this intensity shift. And you penalize now the L1 norm of the modified illumination adaptive optical flow constraint. Here's an example. This is now the army sequence. You see there's some rotation here and some moving. The rubber whale is also present here. This is the ground truth solution. This is now the solution we get with this model. And this is the V function. Look here, for example, here's a moving shadow. Oops. Do you see it? Here the shadow is moving. And this is exactly kept now in this V. So before the optical flow constraint is measured, this part is added to the optical flow constraint, and the regularization here of the TV of V ensures that this is a valid region here. And this is actually the model that the companies are usually using of our library, because this is very robust, and sometimes you can even make use of this information to change the illumination of your movie and so on. Did this answer your question?
I guess so, yeah.
Good. There are other possibilities as well. So, for example, something you can do, you just, instead of I tilde, you take the gradient of I tilde and make everything on the gradient, on the Hessian, whatever you want. So just applying high-pass filters. Yeah?
Do you happen to know, I think Sony produced a phone where you could take three-dimensional pictures.
Yeah.
Basically time to try to make three-dimensional pictures. Did they also use these kind of algorithms? Or?
I'm not sure which exactly they are using, but I guess so, yeah, very similar, I guess so, yeah. Because from the optical flow, when you know the motion of your camera, you can easily get a 3D model.
Yeah.
Okay, now let's move to 3D reconstruction. So when your images I1 and I2 in the optical flow, if they come from a moving camera, or they come from a rectified stereo rig, then actually you can make use of epipolar geometry and determine that the displacement of the optical flow lies on epipolar lines. Yes, it means you can restrict the two-dimensional displacements to one-dimensional displacements on the epipolar lines. So the epipolar lines is actually when you have a stereo setup, you have a pixel in one image, you know that this corresponding pixel has to lie on a line in the second image. Just simply by drawing a triangle through the object point, the pixel point, and the camera center, you easily see that when this triangle intersects your image plane, you get a line. This is the epipolar line. So it means if we know that actually we have a rigid scene, only the camera is moving, or we have two cameras like our two eyes, we can restrict the optical flow to one-dimensional. And if we rectify the images, we can even assume that the displacement is horizontally. This is then called rectified stereo pair. And then based on the displacement, we can compute the depth based on the baseline and the focal length of the camera divided by the displacement. So as I said, it's inverse proportional to the disparity shift. The depth is inverse proportional. And this is some work we did some years ago with Daimler. Daimler is doing a lot with autonomous driving. And we implemented a total generalized variation, regularized optical flow algorithm for stereo. And with this, you can get this kind of nice disparity maps. Then it's a little bit too high on the screen. It's seen much better. But you see that the street is very nicely reconstructed, and it works very well. It also works well with wipers. See that the algorithm, of course, gets crazy if the wiper crosses the screen, the windshield, but it also works very well. Even in night, it worked quite well, although now it's much more complicated in a night scene. And then we did also some experiments where we tried to estimate the distance of objects from the camera, and we evaluated this against a laser rangefinder. And we have seen that actually the distance we have computed in this small square was very accurate against a laser rangefinder. Another PhD student some years ago, he also used this TGV optical flow thing for shape from focus. This is quite interesting. So if you have an object in the microscope and you're changing the distance of the microscope to the object, then every one of you, if you have ever looked through a microscope, you know that everything is blurry except a small region where the part of the object is in focus. And you can make use of that. You are sweeping through different focal length. So this is, I think it's seen in the video now. You see only part of the image is in focus, is sharp, and the rest is blurry. And then you define a sharpness function that gives you now for each 3D position, black means this part of the image was sharp and the rest was not sharp. And this defines then a cost function you use instead of the optical flow constraint, and then you just run the optical flow algorithm in this space. And this kind of 3D objects they wanted to reconstruct, they are well modeled with piecewise affine functions, and therefore the TGV regularizer was quite well suited, and I think in the meantime this is even in their product involved. So they're doing now very accurate, up to a few microns 3D reconstructions of objects using a microscope. So this was still 2.5D. So if you have a depth or range image and you elevate it, you get, this is so-called 2.5D because each point is just elevated and then a surface model is created. But now we are interested in true 3D models. And this is some work I did together with Christopher Zach also some years ago. The idea is that you have a volumetric representation of your object as an implicit surface, and you have different depth images taken from different sides of the object. And now the idea is how can I generate a nice 3D model based on these noisy observations. And the idea is the following. You convert each of these depth images into signed distance 3D functions, where the signed distance function is 0 exactly at the distance, and it's plus or it's greater than 0 in front of the object and less than 0 behind the object. So it's a bit more involved, but I hope you can get the main idea. The thing is the following: you generate many of the signed distance function in a 3D volume, each coming from different depth images. And now you're trying to find a coherent signed distance function, which then looks like this. So this is just visualizing two slices in this 3D volume, which is denoised by the total variation and is also close to this initial signed distance function using the L1 norm. And this worked very well. So we were taking many images of the sequence here, and then the U 3D function looks like this. You see it's a signed distance function. The 0 level set is somewhere here, and if your threshold is at 0, you can extract the 3D object. And I had a very good master and PhD student, Gottfried Grabner, and he even made this thing to work in real time. So what he was doing, he had a webcam browsing the scene, and then from the camera he was computing depth maps, and those depth maps were then projected into this volume and denoised using the total variation. And you see, for example, this part is now seen, now it's reconstructed. You also want to reconstruct the backside of this, and now it should be generated. And after some time, actually you get a very nice 3D model, and everything runs in real time because it's implemented on the graphics card. Here you see actually the noisy depth maps that are generated, but you have many of those noise observations that you get a nice 3D model in the end. Part here is even missing. So it's getting better and better. And finally, you can also put the texture, which you have seen in all these images, put it onto your 3D model, and then you have an online 3D reconstruction here. Oops. Okay. So as I said, I'm much too slow. So it means I need to skip something. So maybe the question is, do we want to know more about more mathematically involved stuff like curvature, or do we want to know a little bit more about learning? I knew it. Who else? Who is for learning? Who is for more mathematical stuff? I would like to do both, but maybe I tell you just 5 minutes about the more mathematical stuff, and if you're interested in that, I can.
Would you be able to provide
the slides? Yes, you will get the slides. Yes. So I'm just talking. I'm skipping this. This is a lot of theory for not working models. It's only it's basically the Mumford-Schaaf functional of this famous person, which is a funny model. It makes a distinguishing between jump part and smooth part, not implicitly handled like in a total variation. And what they are doing, they solve this problem in a higher dimensional setting. So instead of optimizing for the image, they say the image, it's a graph, and they're optimizing for the surface of the graph. And with this, you can make it convex. It's a fun idea, blah, blah. So this is the graph of the function, and you're optimizing directly for this 3D object as a binary. It's like a segmentation. You can also do multi-label segmentation with that. Multi-label image segmentation, yes. You can also do this soap bubble stuff, because with this you can nicely make minimal surfaces with many labels. So when you take this wireframe, put it into this soap water, it generates this shape with a small square in the middle, and we try to get the same simulation on the computer with our convex model, and you see you exactly get this with this small square here inside. Of course, the square can be differently oriented, but by introducing a small anisotropy to your problem, you can get a unique solution of the square. Practically, for computer vision, what is interesting of this lifting approach of the Mumford-Schaaf function to the three-dimensional setting is that for stereo, you can get rid of the image pyramids of optical flow, and you can really compute a globally optimal solution. But it means you have to solve your problem in a 3D space instead of just on 2D images. And it turns out whenever you have a function where the Lagrangian just depends on the function u itself and the gradient, and this function is convex in the gradient, it can be convex in u, but it must be convex in the gradient, then you can compute a globally optimal solution by lifting this problem to a higher dimensional setting and solving it there. So this is some work we did, you see, already some years ago, but still it is used and works quite well. So for example, I did, together with a PhD student, nice 3D reconstruction. This is the city of Graz. Here is one of the main squares, the Jacomini-Platz. When you just do a local matching in stereo without any total variation regularization, you get very noisy depth maps. With TV, you get much better results. Of course, it would be much better with TGV, but TGV does not fit this model here. So it's just first-order derivatives that are allowed. And once you have done this nice 3D model, you can make this virtual fly through Graz. And yeah, give quite good results. I'm just talking maybe 7 minutes about the next thing, and then I'm coming to the learning. Okay, subjective boundaries. Everyone knows what's a subjective boundary? Subjective boundaries are edges you and me, hopefully all of us, see when you look at those images. So when you look at this image, your brain gives you these missing edges here, right? You see this kind of banded square. And the reason is that there's something which nobody knows, but is implemented in your brain that inpaints this edge information. Because for you, the main reasoning behind it, that there's a white square that is in front of these black disks. And by resolving these occlusions, your brain creates these boundaries, and they're called subjective boundaries. So this is well known, it dates back to Canissa's work in the late 70s. So when you look to this image, is there anybody who sees what this is? Don't say it, but maybe raise your hand if you see the object here. Usually, so 5% of the audience can recognize it. You know, I iteratively made it more difficult and more difficult until I reached this 5% in my talks. Nobody sees it? You see it? Tell it? Yes, look, 5%. So we have a good visual system. But it's also funny when I give you some higher level information, let's say every one of you has this object and you use it maybe every day. So if you have this high level information, then you can infer the solution about this. Actually, yes, what your brain was doing, it was trying to connect these missing boundaries to get a reasonable object. And once you have seen it, now everyone sees a bike, right? Now it's very easy to see. And this is somehow the motivation for better models for image regularization, because it turns out that the continuity of edges is important. In the total variation, we just counted the jumps, more or less, in a discrete way. We counted the jumps, but we never said that an edge should be really smooth or should have a low curvature. Namely, it turns out that these missing boundaries here, they can be very well approximated with elastic curves. And the elastic curves are curves that minimizing the elastic energy. So in the elastic energies, you integrate along your curve, forget about the 1 and the alpha, the squared curvature. Okay? And this is the energy that is used when you bend a thin rod. And if you bend a thin rod, the curve, the bended rod is taken, exactly minimizes this elastic energy here. And therefore, what I tried in the past years is somehow to get a reasonable, in the best case, convex regularization functional that penalizes if the object boundaries have too much curvature. So it means if you have a straight object boundary, like the boundary of this table here, this has 0 curvature, then it makes a strong bend here, then 0 curvature, and so on. This chair has small curvature along the boundary, so it favors smooth boundaries. And this is also related to work of the Nobel laureates, Hubel and Wiesel of '59. They obtained the Nobel Prize. I think it was in medicine. They opened the brain of cats and dogs and rabbits, I don't know, whatever they did. And what they showed is that the brain, the visual cortex, has orientation sensitive layers. So certain parts of the brain were firing according to a certain orientation of a pattern they showed the cat. So for example, this layer here fires exactly if the edge is aligned with a certain direction and so on. And then you have many of those layers, and each of those layers in your brain is sensitive to a certain edge orientation in the image. And now if these layers are connected to each other, you can get a sense of curvature. Because if you know that one part in the image is oriented like this, the next one like this, by taking the difference, you actually get the curvature, the difference of the orientations. So therefore, there's some evidence, biological evidence, that also the human brain has a sense of curvature. And this is somehow the inspiration for our model. And this is also used a lot in mathematics. The basic idea is to keep the local orientation of the boundary as a separate variable. So in the total variation, we just had the gradient, and we took the norm of the gradient. So we threw away actually the orientation of the gradient. But now the idea is to keep the orientation of the gradient as a separate variable. This is connected to a Gauss map, where this is the local orientation, to varifolds, so very complicated concept in variational analysis. And in image processing, the idea is to represent image boundaries or gradients in the rotor translation space. So it's a space, you take the image domain and the third dimension, which is the local orientation. Okay, so a gradient is then lives according to its orientation in a different 3D coordinate. I will show an example soon. There's also a sub-Riemannian structure that is then connected to this rotor translation space, which has been used to describe the geometry of the visual cortex. There are many works who made use of that. Okay. So I guess every one of you knows this. If you have a parametrized curve in the space, for example, x1 of t and x2 of t is cosine of 2 pi t and sine of 2 pi t, then you're describing for a parameter t between 0 and 1 a circle, right? And the arc length variation is given by taking the derivative with respect to the parameter of this guy here and taking then the 2 norm. Okay? And this gives you then actually, so if this is your x vector, then the derivative gives you the tangent vector, and the magnitude of the tangent vector is then your arc length. And the tangential angle is then just the angle of this tangent here. Now the curvature of this curve is defined as the ratio between the variation of this tangent angle d theta and the variation of the arc length, d theta over ds. Now you can multiply by 1 both sides, so it's d theta over d theta over ds over d theta. And now you see that this part here can be replaced with this one. So it's exactly the derivative of the angle with respect to the parameter divided by the arc length. Okay? For the circle, for example, if you take this integrate, you exactly get 2 pi times the radius. So now what about this rotor translation space? Now the idea is that we keep this tangential angle as a separate variable, it's the third dimension. And now the circle appears as a helix in 3D. Because also, when you're moving across here, the orientation changes, so it's in a higher 3D position, actually. So now when we compute the arc length of this curve in this 3D space, which is now simple, you take the derivative, take the L2 norm, then you can move out this part from this square root here, and you see, okay, this is nothing less than the arc length, and the guy that remains here is 1 plus, and this is exactly the squared curvature. So it's exactly this part, the curvature, appears here squared. So it means when you embed an object boundary in this rotor translation space, you're already measuring something based on the curvature. So this suggests that this is a good space. And since I don't have enough time, I need to skip a little bit the theory about it. It turns out that many convex functions based on the curvature can be realized in this space. It is the absolute curvature, 1 plus alpha times absolute curvature, then something we call the total rotor translational variation. It's 1 plus square root of 1 plus alpha squared curvature, and we can also get the total squared curvature, which is the original elastica. It's 1 plus curvature squared. And we get this interesting function here, which is quadratic over linear. And quadratic over linear is still a convex function. So it's a very nice function, but it's still a linear function, convex function. So it turns out all these energies are convex energies in this measure based on this normalized tangent vector tau, and with this one-dimensional Hausdorff measure restricted to the curve. Yeah, and then there's I think I cannot go into details here. It turns out we can rewrite everything in this space as a convex energy. There's also some sort of relaxation, so at some point we need to give up certain constraints such that we only get a convex relaxation, which can introduce some artifacts sometimes. So maybe this is not so important, this test here. Yeah, this is a numerical simulation, actually, where we computed our solution in this rotor translation space for a disk, for the boundary of a disk. And actually, this is the vector field we have recovered, and you see this nicely corresponds to this helix for which we have measured this square root of 1 plus curvature squared energy. Here's a nice application for shape completion. So it's known as Weikart's cat. So now I cannot ask you what will be this shape here. It's obviously a cat. The idea is that the image is given in these small dipole areas, black and white, and in the gray area the image is unknown. And now we want to fill the gray area with black or white, such that the curvature of the resulting shape is minimized. And this is actually the result we're getting with our approach here. We still have some issues. You see, it's a little bit blurry sometimes, and this is a discretization issue. We still don't know how to discretize this energy faithfully in order to get good results. So if you're interested in the topic, I would be happy if one of you could contribute with a better discretization based on finite elements or whatever to get better solutions numerically. And this is the original shape. Image inpainting, I already showed you how well or how bad the total variation works. This is now some images where the gray area means the part is missing. With the total variation, it works, but it's very bad. And with this model, it's much, much better, as you can see. So you can even reconstruct these fin structures here because it tries to minimize the curvature. And all these corners that are resulting from the total variation, they have a strong curvature, and so they are recovered by straight lines. Okay, now learning. Maybe I skip this. Let's move here. So in these models we have considered so far, everything is handcrafted based on observations from images. Images should have sparse edges, images should have low curvature edges, and so on and so on. Piecewise affine part in images. So this was just handcrafting. And it turns out that natural images are much more complicated. When I look to the back, these books, they have so many different structures and repetitive structures. So I don't know how to handcraft good models for them. And therefore, an idea is that I consider a very free model with many parameters, and I try to learn those parameters from data. And one of these, there should be normally a video. Okay, it's not there, but it doesn't matter. The model we are considering is the so-called fields of experts model. And the fields of experts model is doing the following. It takes the image, it convolves the image with some filter kernel, and this filter kernel will then be later learned from data, and then it applies a pointwise potential function. This model includes, for example, the total variation. In the total variation, these kernels are finite differences operators, and this rho function is just the 2 norm or absolute function. So as a special case, it contains the total variation, but we will make it much more free. We say that these kernels should be learned completely from data, and they should be much larger, and those functions we will consider different parameterizations. So for the first experiment, we say, okay, what is a good model for these functions? And there's also a paper of Manford and Huang who showed that there's a universal law for the probability density function when you apply a zero mean linear filter to images. Whenever you take a zero mean linear filter, you apply it to images, and you compute its probability density function. Here I took the negative logarithm of it. It will always form this type of heavy-tailed distributions. And this means that in most cases there's no response, and only in a few cases there's a high response. This corresponds mainly to the fact that we have constant regions with sharp edges. But this is a funny universal law for images. And it doesn't matter too much which kind of linear filter you're taking, first, second order derivatives. You can also take what I had here, these discrete cosine transform basis functions. All of these guys, I think here I used one of these filters to generate this curve here. They always have more or less the same shape. And this type of function can be well approximated, for example, with this log 1 plus t squared function with some parameters alpha and beta. So by changing alpha and beta, you can make it more steep, or you can make it more looking like convex. And therefore, one of our first experiment was to learn from data the best filters and the best alpha and beta parameters, such that we can get a good regularizer for image denoising. And how can we do this? And here we used a concept called bi-level optimization. And it's a nested type of optimization problems. The reason is the following. Computing the solution of our model, we need to solve regularization plus data term. It's an optimization problem. So the solution of that minimization problem is itself a minimization problem, but it will be used in a higher level optimization problem, which says if these parameters I'm using here are good to be close to the ground truth images. So therefore the interpretation is the following. We want to find the best filters, alphas and betas, so minimizing with respect to theta, such that the minimizers of our variational model minimizes the square distance to our ground truth solutions. So what is the training data here? We have clean images GS. By adding noise, we can generate noisy images FS. And then this is already a very simple training database which we can use. So how can we compute gradients of the loss function with respect to theta? And the most straightforward approach is to make use of implicit differentiation, but this is heavily time consuming. You need first to minimize this thing, compute the Hessian matrix, invert the Hessian matrix, and then you get gradients of the loss function with respect to theta here. So this is mainly work done by my PhD student, former PhD student, Yunjin Chen. And I was pushing him to make larger and larger experiments, and the biggest experiments he did was to learn 80 filters, each of size 9 times 9, plus these two function parameters. In total it was 6,500 parameters. And this took, in his MATLAB implementation, 2 weeks, and this is what he then found. And the most funny thing is when you look at the first 2 filters, these are exactly the total variation filters. Find the differences in horizontal and vertical directions. And they are ordered by the importance. So it means the total variation is not a bad model, it's just missing a few higher order terms. It's missing 78 filters. And on the right hand side you see the corresponding potential functions. You see some look more like L1, some are more like concave, some are even quadratic, and this shape is obtained by choosing different alphas and betas. This can change the shape of this function here. At this time we evaluated it against the state of the art, and it turned out that it worked very well. So there was just a very complicated model based on non-local patches, sparsity, whatever. Took hours to compute, and ours just took a few milliseconds, I think. So here's a comparison. There's a noisy image. This is how a typical TV denoised image looks like, and this is how the learned image looks like. So you see there's a tremendous improvement for natural images by learning from data. Of course, we cannot get back to the true image. If you have a noisy image, there's no chance to get back to the true image. There's always some ambiguity. But still, I think that the result is quite well. Okay, so one problem with this approach in 2014 was that it was based on bilevel optimization, which is heavily time consuming. As I have mentioned, you need to solve the lower problems exactly in each step before you can compute the gradient, invert the Hessian of the lower level problem, and then it also turns out that the performance of the learning very much depends on how accurately you solve the lower level problems. And then we had a different idea. We said, okay, we give up the fact that we want to solve the lower level problem exactly. We rather say, okay, let's perform 10 or 20 iterations of a gradient descent algorithm that minimizes the lower level problem, and we just use the last iteration instead of the true minimizer. And by doing so, we here get a recursive, definition of the iterations, a nested function, and we just use the last iteration here. And for this formulation, it turns out that you can compute the exact gradient without this implicit differentiation by means of backpropagation. You just make, you make it forward and you make it backward and use the differentiated functions. Additionally, it turns out we did not have to perform many steps. It even worked better if we limited the number of steps here. So if we just said we want to do 10 steps, it already worked better than doing 20 steps. And the reason is that from inverse problems, maybe some of you know that something like early stopping, if you solve the inverse problem, you should not optimize too much. You should stop at a certain time, and you get better results. And then we made this scheme even more flexible by allowing to change the filters and the potential function in each iteration. So this is something done by Jungjin and then later by Erich Kobler, where we allowed the filter kernels and the potential functions, these 5 functions are just the derivatives of the potential functions, to change in each iteration. So each iteration now had new parameters. And this increased the flexibility of the scheme quite a lot. And it also allows you to interpret the scheme as a particular type of convolutional neural network. So now by unrolling the steps of this gradient descent algorithm, you see what is it doing. It convolves the image with a filter, applies a nonlinear function, which is the derivative of the potential function, then convolves it again with the rotated kernel, which is the adjoint operator, and adds the gradient of the data fidelity term. And this is a very close structure to so-called residual convolutional neural networks, which are considered to be the most stable neural networks in image recognition. Okay, so without going too much into details, we are using now this type of model quite a lot for different applications. Here I'm showing you some experiments where I learned it on approximately 400 images, and the filters are of size 11 times 11, and I use different constraints on the filter kernels, like the 1 norm or the 2 norm, using the fact that I can rotate filters or not. And I show you some results here. So we learned just 5 steps, and this is how the filter kernels look like when I allow them to be rotated. It means I just learn the first kernel and then also apply the rotated versions of the kernels. Here you see the derivatives of the potential functions that correspond to these kernels. You can also use L1 penalization of the kernels during learning, then you get sparse kernels. You see here I used L2 norm, here I use L1 norm, you get much sparser kernels, but the performance did not change at all. It just gives you a different solution of the model. And we also tried without orientations, but then we need much more filters to learn, much more parameters. So here the number of parameters is just 5,000. Here we need 27,000. And again, the same performance. So now I'm showing you the 5 steps of the algorithm, what it is doing. 5 iterations of a gradient descent with changing parameters. Initialization, first step, second, third, fourth, finished. So after 4 steps, you get really nice results. Now again, a comparison. TV denoised, this was the 2 weeks model, still an optimization problem, and this is the 5 steps model. And now you see that with this we were able to even get better results. we have also evaluated this, and it works very well, and is extremely fast to compute, just making 5 steps. Yeah?
How did you arrive at 5 steps? Like,
just write it out. It gives you slightly better when you do 7 steps or 10 steps, but with 5 it already works very well. So adding more steps does not make the problem worse. This is now work of another PhD student, Kerstin Hamanik. He applied this scheme for Mri reconstruction. I already explained to you Mri reconstruction in the beginning. In this Fourier domain, parallel imaging, linear operator, and so on. And now the idea was, okay, let's try to learn a model that can do Mri reconstruction. So for this, it was a bit more complicated to get ground truth data, but we are working together with the New York University, with Michael Recht, Daniel Sodiksen, and Florian Knoll, and they acquired fully scanned MRI scans, which costs actually a lot of money because it takes much more time. Time is money for scanning. And with this, we were then able to train our models. And here the idea was we would like to get reconstructions by using only a sub-part of the data and get the best reconstructions out of that, which are as close as possible to the fully scanned data. So just by taking every 4th or 6th line in the Fourier domain, getting the same quality results as taking every line in the Fourier domain. So this was our learning task. Here are some of these filters and functions. Look quite similar to the previous ones. And now I'm visualizing the 10 steps of the algorithm, and it does crazy stuff. We still don't understand what it is exactly doing. So this is the initialization. First stage, second. Then it's doing this. So it's doing like oscillations. It's adding some frequencies, removing these frequencies, adding and removing. This. Next one. Again, strange. And this is the final result. And we have evaluated it against the state of the art, and it was always the best method, and it was also very fast, a few milliseconds. And here some comparisons. This is when you don't do regularization at all. Of course, it's not usable, this result. This is the clinical standard. It's just minimizing the data fidelity term without regularizer. It's called CG Sense. So every Siemens scanner has implemented this algorithm. This is when you use total generalized variation, or TV. Give you a very similar result. And this is what you get with this learned algorithm. So you see that it is much better. When you compare it to the fully sampled scan, you see you're still losing something. But of course, I mean, using less data, you cannot say you can get exactly the same quality. But we did some tests with medical doctors. They had to detect the pathologies in these images, and they arrived at exactly the same result as using the fully scanned. So it is good enough for them. And it was acceleration factor 4, so it's only 1/4 of the time to scan this, to make this scan. This is another contrast. I think this is now positron density, coronal fat saturated, clinically standard, TGV, and this you get with the learned one. And this is what you're missing with respect to the reference. A little bit of contrast, but it's the best you can get out of the data. Okay, so 3 minutes left. Just very quickly, some very recent work with PhD student Patrick Knöbelreiter. The task here is to do a denoising of disparity maps for stereo. And we do this by collaborative filtering, collaborative denoising. So collaborative means we jointly denoise the depth map. We have also computed kind of a reliability measure of the matches, or confidence measure, how confident is a certain value here, and the color image. It's a regularization term that is defined in this, 5-dimensional vector valued image that consists of the 3 RGB planes, the confidence planes, and the disparity plane. And this is how the initial disparity map, confidence map, and color image looks like. This is an intermediate state, and this is the final output. And maybe I should say how this initial depth map here is generated. What we're using is a deep network that is trained to compute image descriptors. So it means matching from the left and the right image. I'm not showing the second image here, but it's just a stereo pair. We computed a convolutional neural network that computes an image descriptor such that we can reliably match those two images. But still, in occluded regions, there are a lot of outliers, and there are also some wrong matches at edges and so on. And based on the matching cost, we have derived a confidence measure. We also used some geometric constraints to detect if there are occlusions in which we lower the confidence measure to be 0. Now the idea is to jointly denoise all these three guys. And the idea is, if we have an object boundary, then there should be also a boundary in the disparity map, because an object causes a depth discontinuity. For example, here are some boundaries which are not visible here because this is based on an occlusion. And additionally, the confidence measure should be used to tell the algorithm in regions where the confidence is 0, there should be more in-painting, and in regions where the confidence is almost white, it means this is a reliable match, so the algorithm should trust those disparity values. And now I'm visualizing these three different steps. So this is the initial, this is the first step. You see the color image is strangely modified. And then it starts to do a joint denoising. And this is the final result. So, and we are quite happy with this result because you see all these artifacts and noise are actually gone. And interesting, the color image here is somehow abstracted to just keep the main edges, which are also visible here. And also the confidence measure is refined. You see around depth discontinuities, it is lowered. And we did also some evaluation that actually the new confidence measure is much more reliable than the original confidence measure. Here's a second example, which with a much harder scene, where the rectification of the image is slightly off, so that the initial matching is a little bit more complicated and produces many outliers. And these are then the 7 steps of the algorithm. And it can denoise that much noise in the image, so we are quite happy. And when you look to these abstracted color images, you really see what this algorithm is trying to do, to abstract the color images, to extract the main edges and use them to denoise this image here. Final comparison, this is the initial disparity map. You see it's really wrong because it's very hard to compute stereo matches on the car. You have specular highlights, reflections. It's even hard for a human. This is when I use a total variation denoiser, where I even used color edges and I used the confidence measure, and this is the result you're getting with this learned scheme. So you see how it can nicely get the shape of the car, and it turns out that the quality of this is even worse compared to the quality of this. Okay, so we are done. So I was talking about, for me it's already a more than 10 years journey, and I was also talking about old work of mine. And so for me, what I have seen, starting with traditional variational models with handcrafted prior terms, they work quite well for many applications. But in the end, they're still too simple really to capture the statistics of natural images. So natural images are much too complex. Maybe for disparity images, optical flow, fields, these handcrafted regularizers work well, but natural images are much more complicated, and therefore we need some sort of learning there. All these models are defined by means of an optimization problem, so computationally they can be quite expensive. And in the end, you should ask yourself, and this is what I'm asking myself, if you have a bad model, does it really make sense to accurately optimize a bad model? So if the modeling error is higher than the optimization error, then it doesn't make sense to really accurately optimize this model. And we are now slowly moving to this kind of learning approaches, which we termed variational networks, because their structure is inspired by variational approaches. So they still have a gradient and filters and functions, so we can still interpret what these networks are doing. They can be interpreted in different ways as incremental gradient descent methods, like kind of neural networks and so on. They are much more flexible, very low in their computational cost, but unfortunately almost no theoretical research so far, so we are really working on that. So it's still completely unclear what's the right mathematical setting to study properties of these kind of schemes. But what we have seen is that we are adding structure to the models, like saying that the filters can be rotated or they live on multiple scales. Helps a lot to find good models with fewer parameters. So mainstream deep learning, they often have hundreds of millions of parameters, and we mostly have just a few thousand of parameters. But in the end, these learned methods outperform handcrafted models by a large margin. So, and this is more or less the way I continue my research. I'm still not clear where this will bring us up, but I have seen learning is really important to get better models. And I think this is not limited only to computer vision and image processing, inverse problems. I think to almost any kind of computational science where you need to build up models. Maybe learning the models from data will help you to get better models, but still you would like to keep the interpretability of the models. And this is somehow this, I'm living between these theoretically well-established methods and the methods that perform well in practice. I'm trying to be in this gap. Unfortunately, this gap seems to increase. With this, I would like to thank you for your attention. So if you have any questions, feel free to talk to me now or write me a mail, or if you're interested to come to Graz to visit our group, you're welcome, of course. I will also be here in the afternoon. And as I said, the slides will be made available to you. So if you have any questions, feel free to ask. Thank you very much.